Welcome to our deep dive into the fascinating and somewhat perplexing world of cosmology. Today we're exploring an emerging crisis in the field that challenges our understanding of the universe. Cosmology, the study of the origin, evolution, and eventual fate of the universe, is a cornerstone of modern physics and astronomy. It connects broad philosophical questions with precise scientific observations. Historically, cosmology has passed through many phases. From the ancient models of the cosmos to the revolutionary shift brought by Einstein's theory of general relativity, each step has greatly expanded our understanding. Yet today we find ourselves at a crossroads, facing discrepancies that current theories cannot fully explain. This crisis is not just a minor hiccup, but a major challenge that could redefine future research and theoretical foundations in cosmology. The stakes are high because the answers could lead to new physics, transforming our understanding of everything from the microscopic world of particles to the vast expanse of the cosmos. In the next few hours, we will unfold the layers of this crisis. We'll explore the key problems like the Hubble tension, the mysteries surrounding dark matter and dark energy, and the peculiar observations that current theories struggle to explain. Each of these issues points to potential cracks in the very foundation of our cosmic understanding. Our journey will take us through the depths of theoretical physics, challenging the robustness of Einstein's principles and questioning the completeness of quantum mechanics as we push the boundaries of known science. We delve into alternative theories that attempt to resolve these cosmic conundrums, including modifications to our understanding of gravity itself. The tools we use to observe and interpret the universe are also at the forefront of this exploration. Advances in technology have provided us with data of unprecedented accuracy and volume, offering new insights and raising new questions. The James Webb Space Telescope, the Event Horizon Telescope, and other instruments are crucial characters in this story. We'll see how these tools not only enhance our capabilities to observe the known, but also help us venture into the unknown, testing the limits of our theories and sometimes revealing their shortcomings. As we gather more data, the tension between different measurements of the universe's expansion rate becomes more pronounced, hinting at new physics or unknown facets of the cosmos. Throughout this exploration, we'll also consider the philosophical implications of these scientific endeavors. How does our understanding of the cosmos reflect on our place within it? What does it mean for a theory to provide a true description of the universe? We will conclude our journey by looking forward, speculating on how new theories, technologies, and experiments might one day resolve the current crises in cosmology. This will include a discussion on the ethical and philosophical considerations of pursuing such profound questions about our universe. Finally, we will reflect on the importance of cosmology, not just as a science, but as a fundamental human endeavor that satisfies our deepest curiosities about the world around us. As we continue to question, explore, and challenge the cosmos, we keep alive the most profound aspects of human nature, our relentless pursuit of knowledge. Cosmology is the scientific study of the large-scale properties of the universe as a whole. It endeavors to understand the entire cosmos using the best available scientific data and models. The significance of cosmology lies in its ability to provide a physical explanation for the past, present, and future of the universe. This field involves a variety of disciplines including physics, astronomy, mathematics, and even philosophy, merging them to solve some of the most profound questions about the cosmos. By studying the universe's origin, structure, evolution, and eventual fate, cosmology seeks to uncover the fundamental laws that govern the universe. One of the central achievements of cosmology was the development of the Big Bang theory. This describes how the universe expanded from an extremely dense and hot state and continues to expand to this day. It serves as a cornerstone that supports much of the observational science in cosmology. Cosmology also significantly impacts our understanding of matter, energy, space, and time. It examines the dynamics of galaxies and galaxy clusters while exploring the role of dark matter and dark energy, which together compose most of the universe's mass-energy content. The study of cosmology has profound implications, not just for our understanding of the universe, but for the entire field of physics. It tests laws of physics under extreme conditions that are unachievable in terrestrial laboratories. For instance, theories of elementary particles are often informed by observations of the cosmos. Moreover, cosmology raises questions that are inherently philosophical, such as the beginning of the universe and the nature of the cosmos itself. These questions push the boundaries of scientific inquiry and require new theories and methodologies to answer. The observational aspect of cosmology also has significant implications. It utilizes a variety of methods to observe the universe at different wavelengths, from radio waves to gamma rays, providing a comprehensive view of the cosmos. Through these observations, cosmologists have been able to infer the existence of phenomena such as black holes, measure the rate of the universe's expansion, and map the cosmic microwave background radiation, which provides a snapshot of the early universe. Cosmology's interdisciplinary nature has catalyzed collaborations across various scientific communities, leading to significant technological innovations. These include advancements in telescope technology, sensors, and data processing methods, which in turn benefit other fields of science and engineering. It also challenges our understanding of the universe through paradoxes and anomalies that arise from observational data, prompting ongoing debates and research that aim to resolve these issues. This continuous inquiry not only refines existing models, but also occasionally revolutionizes them. Understanding cosmology is vital for educating the public about science and our place in the universe. It addresses fundamental questions about existence and fosters a sense of shared heritage and destiny among the diverse peoples of our world. In teaching us about the universe, cosmology also teaches us about ourselves, reflecting our curiosity and our ambitions. It embodies our quest to explore and understand the universe, from the largest galaxies to the smallest subatomic particles. Cosmology stands at the crossroads of culture, science, and philosophy, making it one of the most dynamic and intriguing areas of human inquiry. It not only satisfies our curiosity about the universe, but also stimulates it, propelling our intellectual capacities to new heights. As we peel back the layers of the cosmos, cosmology not only answers old questions but also generates new ones, ensuring that our journey through the universe is an ongoing adventure. This journey, driven by both observation and theory, continues to shape our understanding of the very fabric of reality. Cosmology has evolved dramatically over centuries, shaped by various cultures and scientific revelations. Initially, ancient civilizations such as the Babylonians and Greeks viewed the universe as a flat Earth or a central Earth surrounded by the heavens. These early models were deeply intertwined with mythology and religion. The revolution in cosmological thought began with Nicholas Copernicus in the 16th century, who proposed that the Earth was not the center of the universe, but rather orbited the Sun. This heliocentric model laid the groundwork for modern astronomy, challenging long-held beliefs and altering our view of the universe. Building on Copernican theory, Johannes Kepler and Galileo Galilei in the 17th century introduced laws of planetary motion and telescopic evidence supporting the heliocentric model, respectively. These advancements underscored the importance of empirical data in shaping our understanding of the cosmos. Isaac Newton further transformed cosmology in the late 17th century with his law of universal gravitation, which mathematically described the gravitational force that governs the motion of celestial bodies. This provided a unified explanation for both earthly and astronomical phenomena. The 20th century ushered in a new era of cosmological discovery with Albert Einstein's theory of general relativity in 1915. This theory offered a new framework for understanding the gravitational forces in the universe, suggesting that massive objects warp the fabric of space-time itself. Edwin Hubble made another monumental contribution in the 1920s by discovering that distant galaxies are moving away from us in all directions. This observation provided the foundational evidence for the expanding universe and led to the formulation of the Big Bang theory. The discovery of the cosmic microwave background radiation in 1964 by Arno Penzias and Robert Wilson offered a glimpse into the early universe, providing critical support for the Big Bang theory. This discovery also opened new avenues for understanding the universe's origins and its earliest moments. In the late 20th century, the development of inflationary theory by Alan Guth and others proposed that the early universe underwent an exponential expansion, solving several puzzles of the Big Bang model. This theory has become a crucial component of modern cosmological thought. The 1990s and beyond saw the surprising discovery that the expansion of the universe is accelerating. This observation, made through studies of distant supernovae, led to the theory of dark energy, a mysterious force driving this acceleration. The detailed mapping of the cosmic microwave background by missions like NASA's Cosmic Background Explorer and later the Wilkinson Microwave Anisotropy Probe has refined our understanding of the universe's structure and composition, providing a detailed picture of the universe just after the Big Bang. Large-scale simulations and telescopes have enabled cosmologists to study the large-scale structure of the universe, revealing a cosmic web of galaxies and dark matter. These structures have provided insights into the distribution of matter in the universe and the role of dark matter in cosmic evolution. The detection of gravitational waves by LIGO in 2015 offered a new method of observing cosmic events, opening up the field of gravitational wave astronomy. This discovery has provided a novel way to probe events like black hole mergers, which are otherwise invisible through traditional telescopes. The Event Horizon Telescope project achieved another milestone in 2019 by capturing the first image of a black hole's event horizon. This remarkable achievement not only confirmed a prediction of general relativity, but also demonstrated the power of global scientific collaboration. Current cosmological research continues to push the boundaries of our knowledge, exploring the nature of dark matter, the properties of dark energy, and the possibilities of multiverse theories. Each discovery and theoretical advancement brings us closer to understanding the deeper workings of the cosmos. As we stand on the brink of new discoveries, cosmology remains a vibrant field of scientific inquiry, continually reshaping our understanding of the universe through a combination of observation, theory, and daring speculation. This ongoing journey reflects our enduring quest to decipher the mysteries of the cosmos. Resolving the current crises in cosmology is crucial for the advancement of the field, because it directly impacts our fundamental understanding of the universe. Without addressing these discrepancies, our models of the universe remain incomplete, potentially overlooking key aspects of cosmic phenomena. The importance of these issues extends beyond theoretical interests. They have practical implications for the technology we develop and the further scientific investigations we pursue. Advanced cosmological models influence everything from satellite trajectories to our broader strategies for exploring space. Furthermore, refining our cosmological models can lead to breakthroughs in other areas of physics. For example, resolving the nature of dark matter and dark energy could have implications for particle physics, potentially unveiling new particles or forces that could revolutionize the field. In addition, clearer understanding of cosmic expansion and the fate of the universe can help us better predict and perhaps even mitigate cosmic threats to Earth. Knowledge of these fundamental aspects of cosmology is not just academic, but a matter of long-term survival and strategic planning. The effort to resolve these crises also drives technological innovation, particularly in areas like telescope design, sensor technology, and data processing. Each breakthrough in observation or theory can lead to new tools and techniques, which can be applied across scientific disciplines. Addressing these issues fosters interdisciplinary collaboration, bringing together astronomers, physicists, mathematicians, and computer scientists. These collaborations enrich each field, broadening the scope and depth of research methodologies and insights. Educationally, engaging with these profound questions sparks interest and curiosity in the next generation of scientists. Resolving these crises provides compelling case studies for educational purposes, illustrating the dynamic nature of scientific inquiry. From a philosophical perspective, understanding the universe challenges and refines our existential and ethical perspectives. As our cosmological models become more comprehensive, they influence how we see our place in the universe and shape our philosophical outlook on life. Financially, clear results and resolutions of cosmological questions can justify the enormous investments in space research and high-cost astronomical observatories. Demonstrating progress can ensure continued funding and support from both public and private sectors. Moreover, resolving these issues enhances our predictive capabilities. Accurate cosmological models allow us to better predict celestial events and understand the universe's long-term behaviors, which is essential for future space missions and long-term planning. Resolving the crisis in cosmology also helps to maintain public trust and interest in science. Demonstrating that science can tackle and solve big existential questions reinforces the value of scientific research and education in society. Internationally, the drive to resolve cosmological issues promotes global cooperation. Many of the facilities and research projects require international collaboration and funding, fostering peaceful relations and shared goals among different nations. Ethically, a deeper understanding of the universe through resolved cosmological models can guide our decisions regarding space exploration, the use of space resources, and our overall approach to the universe, ensuring responsible and ethical conduct in these endeavors. Finally, resolving the crises in cosmology can lead to a new philosophical and scientific paradigm, similar to the shifts brought about by Copernicus or Einstein. Such a shift could redefine humanity's view of reality, offering new insights and possibly even new laws of nature. Each of these points underscores the critical importance of resolving the current issues within cosmology, not just for the advancement of the field, but for the broader impacts on science, technology, philosophy, and society at large. As we continue to explore these questions, we not only advance our knowledge, but also enhance our collective ability to innovate and understand our universe at a deeper level. The Hubble constant is one of the most crucial figures in cosmology because it measures the rate at which the universe is expanding. Named after the American astronomer Edwin Hubble, who made the pivotal discovery in the 1920s, it quantifies how fast galaxies are moving away from each other. This constant is expressed in kilometers per second per megaparsec, which means for every megaparsec, approximately 3.26 million light-years, away from a galaxy, that galaxy is observed to be moving away from us at a certain speed due to the expansion of the universe. Edwin Hubble's observations revealed that galaxies farther away from us are moving faster, suggesting that the universe is expanding uniformly. This was a monumental discovery because it implied that the universe had a beginning, a fact that gave rise to the Big Bang theory. To calculate the Hubble constant, astronomers measure the distance to far-off galaxies and the speed at which they are moving away from us. This speed can be determined by looking at the light from a galaxy and measuring its redshift, which occurs because the light stretches as the universe expands. The precise value of the Hubble constant has been subject to ongoing debate and refinement. Different methods of measurement, using distant supernovae, the cosmic microwave background radiation, or other astronomical markers, have yielded slightly different results. This discrepancy in measurements is not just a minor technical issue. It hints at a deeper crisis in cosmology. If the universe's expansion rate is not consistent across observations, it could indicate new physics at play, such as properties of dark energy, or the behavior of gravity on cosmic scales that we do not currently understand. The Hubble constant not only informs us about the current rate of expansion of the universe, but also helps us infer the age of the universe. A higher Hubble constant suggests a younger universe, while a lower value indicates an older universe. Understanding the Hubble constant is crucial for the study of cosmic phenomena. It affects calculations related to the cosmic microwave background and models of dark matter and dark energy, which together compose most of the universe's total energy density. Refining the value of the Hubble constant also refines our understanding of the universe's structure and history. It affects our models of how galaxies form and evolve, how clusters of galaxies interact, and the future fate of the cosmos. Despite its name, the Hubble constant is not truly constant over time. According to models of the universe, the rate of expansion changes as the dominant forces in the universe change. Early on, the universe's expansion was slowed by gravity, but has since been accelerated by dark energy. This evolution of the universe's expansion rate makes determining the exact value of the Hubble constant challenging. It requires incredibly precise observations and a deep understanding of cosmic history, from the Big Bang to the present. The debate over the Hubble constant embodies the dynamic nature of cosmology. As new observational techniques and technologies emerge, our understanding of this constant and what it tells us about the cosmos continues to evolve. Resolving the differences in measurements of the Hubble constant is not just a question of finding the right number. It is a question of understanding the underlying physics that drives the expansion of the universe, which has profound implications for the fate of the cosmos. Each new study of the Hubble constant offers a fresh glimpse into the mechanics of the cosmos, challenging our assumptions and pushing the boundaries of known physics. It is a key that helps unlock the mysteries of the universe's past, present, and future. Thus, the Hubble constant is more than just a number. It is a fundamental part of our cosmological framework, a cornerstone upon which much of modern astronomy and cosmology is built. In cosmology, one of the most puzzling discrepancies involves differing measurements of the universe's expansion rate, known as the Hubble constant, obtained from observations of the early universe compared to those from the local universe. This discrepancy has profound implications for our understanding of the cosmos and suggests that our current models may be incomplete. Measurements from the early universe are typically based on observations of the cosmic microwave background radiation, the afterglow of the Big Bang. This radiation provides a snapshot of the universe when it was just 380,000 years old, and by analyzing its properties, cosmologists can infer the expansion rate at that time. On the other hand, local measurements are derived from observations of supernovae, Cepheid variables, and other standard candles in nearby galaxies. These objects have known luminosities, allowing astronomers to calculate distances and velocities, thereby measuring the current rate of expansion directly. The discrepancy arises because the value of the Hubble constant derived from the cosmic microwave background tends to be lower than the value derived from local measurements. This suggests that the universe is expanding faster now than what would be expected based on conditions observed in the early universe. Several factors contribute to this tension. One possibility is that unknown types of matter or energy, not accounted for in current models, could be influencing the expansion of the universe. Alternatively, the discrepancy might be pointing to new physics beyond our current understanding of gravity and the standard model of particle physics. Another consideration is the role of dark energy, a mysterious force that is driving the accelerated expansion of the universe. If dark energy has evolved over the history of the cosmos, this could explain why the expansion rate appears different when measured at various epochs. Measurement errors and biases could also contribute to the discrepancy. Astronomical measurements are incredibly complex and sensitive to the methods and instruments used, meaning that subtle biases could lead to significantly different results. Improvements in technology and methodology are continually refining these measurements. As telescopes and sensors become more sophisticated, astronomers are able to reduce uncertainties and cross-check results using different observational techniques. Cosmologists also use computer simulations to model the universe and predict what different measurements should be, based on various theoretical assumptions. These simulations help identify which theories are most consistent with observations and where new theories might be needed. Another approach to resolving the discrepancy involves looking for independent ways to measure the expansion rate, such as using gravitational waves as cosmic rulers. This method has recently become feasible with the detection of gravitational waves from merging neutron stars, providing a completely new way to measure cosmic distances. The debate over the Hubble constant is not just academic, but has real consequences for our understanding of the universe. Resolving it could lead to a better understanding of cosmic history, from the Big Bang to the present, and even predict the future trajectory of cosmic expansion. The ongoing research into this discrepancy is a vibrant area of cosmological study. It brings together a wide range of disciplines, from theoretical physics to observational astronomy, each contributing insights that could help solve this puzzle. Ultimately, the resolution of these differing measurements may lead to a new understanding of the fundamental forces that shape the cosmos. Whether it involves new particles, forces, or a new theory of gravity, the outcome will likely revolutionize our understanding of the universe. As we continue to explore these discrepancies, cosmology remains on the cutting edge of scientific inquiry, pushing the boundaries of what we know about the universe and our place within it. The pursuit of these answers not only deepens our understanding of cosmology, but also drives technological and methodological advances that benefit all of science. The discrepancies in measurements of the Hubble constant have a profound impact on cosmological models, calling into question our understanding of the universe's fundamental properties and dynamics. These models rely heavily on precise constants to predict everything from the behavior of galaxies to the ultimate fate of the universe. A higher Hubble constant, as suggested by local universe measurements, implies a younger universe. This requires adjustments in cosmological models to account for how stars, galaxies, and other cosmic structures could have evolved more rapidly than previously thought. Conversely, the lower Hubble constant derived from observations of the early universe suggests a slower expansion and an older universe. This scenario allows for more time for cosmic evolution, but challenges theories about dark energy and the rate of acceleration of the universe's expansion. These conflicting measurements force cosmologists to reconsider the balance of matter, and dark energy in the universe. The standard model of cosmology, known as the lambda CDM model, which includes a cosmological constant, lambda, and cold dark matter, CDM, is based on a specific rate of expansion. If the rate of expansion is different, it could mean that dark energy behaves differently than the cosmological constant, perhaps changing over time. This would have significant implications for the model's predictions about the future of the universe. Moreover, discrepancies in the Hubble constant could indicate new physics beyond the standard model of cosmology. This could include new particles, forces, or modifications to gravity, necessitating a revision of our most fundamental theories. The impact extends to our understanding of cosmic inflation, the rapid expansion of the universe that is believed to have occurred just moments after the Big Bang. Inflationary models are tightly linked to the expansion rate. Different rates could support different versions of inflation or require entirely new theories. These discrepancies also affect precision cosmology, where accurate measurements are used to test the limits of physical theories. Uncertainty in the Hubble constant translates into uncertainty in other measurements and tests, potentially skewing our interpretation of cosmological data. This situation creates a need for more sophisticated models and simulations that can accommodate a range of expansion rates and their implications for cosmic history. These models must be flexible, yet robust enough to provide accurate predictions under varying assumptions. Resolving these discrepancies is not just about adjusting numbers, but about enhancing our conceptual framework for understanding the universe. It drives theoretical innovation, as new models and ideas are proposed and tested against observational data. The discrepancies also stimulate the development of new observational techniques and instruments. As astronomers and physicists strive for more precise measurements, they push the boundaries of technology, leading to advancements that benefit other fields of science. Internationally, this challenge encourages collaboration across borders. Resolving such fundamental issues requires pooling data, resources, and expertise from around the world, fostering a global scientific community. Ethically, it underscores the importance of transparency and rigor in scientific research. As cosmological models have wide-ranging implications, ensuring that they are based on the most reliable data and interpretations is crucial for maintaining public trust in science. Educationally, these discrepancies provide a valuable teaching tool, illustrating the dynamic and evolving nature of scientific understanding. They show that science is not just about finding answers, but also about asking better questions. In summary, the impact of discrepancies in measurements of the Hubble constant is broad and deep, affecting not just cosmological models but also the philosophical, technological, and ethical foundations of science. As such, resolving these discrepancies is a central endeavor in modern cosmology, crucial for advancing our understanding of the universe. Dark matter and dark energy are two of the most elusive and fascinating components in cosmology, playing critical roles in our understanding of the universe. Despite their importance, both remain largely mysterious and are defined primarily by the effects they seem to have on cosmic structures and phenomena. Dark matter is a type of matter that does not emit, absorb, or reflect light, making it completely invisible to current detection methods that rely on electromagnetic radiation. It is defined through its gravitational effects on visible matter, such as galaxies and galaxy clusters. Without dark matter, the gravitational pull exerted by visible matter would be insufficient to hold galaxies together as they rotate at observed speeds. The role of dark matter in the universe is crucial for the formation and stability of cosmic structures. It acts as the scaffolding for galaxies and galaxy clusters, dictating their shape and aiding in their formation by providing enough gravitational force to counteract the expansive forces of the universe. Dark energy, on the other hand, is an unknown form of energy that permeates all of space and tends to accelerate the expansion of the universe. It is defined by its property of having a strong negative pressure, which is theorized to be responsible for the observed acceleration in the cosmic expansion rate. The role of dark energy is not just to accelerate the expansion of the universe, but it also influences the fate of the universe. Depending on the true nature and behavior of dark energy, the universe might continue to expand indefinitely, slow down, or even collapse back on itself. Together, dark matter and dark energy compose about 95% of the total mass energy content of the universe, with dark energy taking about 68% and dark matter about 27%. This overwhelming dominance in the universe's composition makes understanding them critical for a complete picture of cosmic dynamics. Despite their critical roles, both dark matter and dark energy are detected only indirectly. For dark matter, this detection comes through its gravitational effects on visible matter and the bending of light, a phenomenon known as gravitational lensing. For dark energy, its presence is inferred from measurements of the expansion rate of the universe, using distant supernovae and the cosmic microwave background. Theoretical models of dark matter include weakly interacting massive particles, WIMPs, and axions. These particles have been hypothesized based on extensions of the standard model of particle physics, but have yet to be detected directly, making them subjects of intense research in both cosmology and particle physics. Similarly, theories about dark energy range from the cosmological constant, a constant energy density filling space homogeneously, to more dynamic fields such as quintessence, which vary in time and space. Each theory attempts to explain the observed properties of dark energy and its impact on the universe. The search for dark matter and dark energy is not only a quest for fundamental understanding, but also a driving force for technological advancement in detectors and observational techniques. It pushes the boundaries of particle physics, astronomy, and quantum mechanics. Moreover, the study of dark matter and dark energy has significant philosophical implications, challenging our notions of what constitutes matter and energy. It also tests the limits of our scientific methodologies and our ability to understand the universe. In summary, dark matter and dark energy are central to cosmology, defining the structure, evolution, and fate of the universe. Their mysterious nature and dominant role continue to inspire some of the most profound questions in modern science, driving a wide range of research activities aimed at unlocking the secrets of the cosmos. As cosmologists and physicists work to elucidate these components, they not only deepen our understanding of the cosmos, but also refine our theories and models of the universe, contributing to the broader field of physics and enhancing our grasp of fundamental forces and particles. Exploring these dark components is therefore not just about understanding the cosmos, but also about expanding the frontier of human knowledge, probing the universe at its most fundamental level, and challenging our understanding of the very fabric of reality. Detecting dark matter is one of the most formidable challenges in cosmology and particle physics. Despite its significant gravitational influence on visible matter, dark matter does not interact with electromagnetic radiation, which means it doesn't emit, absorb, or reflect light, making it invisible and extremely difficult to detect using conventional methods. One of the primary methods scientists use to search for dark matter is through direct detection experiments, which aim to observe the rare interactions between dark matter particles and normal matter. These experiments often take place deep underground or in isolated locations to shield them from cosmic rays and other forms of background noise that could interfere with the detection of subtle signals. Indirect detection efforts focus on capturing the byproducts of dark matter interactions or decays that might occur naturally in space. For example, if dark matter particles can annihilate each other, they might produce gamma rays, neutrinos, or other particles that can be detected by high-sensitivity instruments. Another approach involves the use of gravitational lensing, a phenomenon where the gravity of a massive object, like a cluster of galaxies, bends the light from objects behind it. By studying the bending of light, astronomers can infer the presence of mass, including dark matter, even if it emits no light. Theoretical physicists are also contributing to the hunt for dark matter by proposing new models that predict different types of dark matter particles, such as axions or sterile neutrinos. These models help guide experimental searches by suggesting what properties these particles might have and how they might be detected. Despite these efforts, dark matter has eluded direct detection so far, leading some scientists to consider even more novel methods. For instance, researchers are exploring the possibility that dark matter might affect the fundamental constants of nature in measurable ways. One of the biggest challenges in detecting dark matter is distinguishing potential signals from background noise. The interactions of dark matter are predicted to be so weak and rare that distinguishing them from random fluctuations in the data is a significant hurdle. Technological advancements are crucial in this quest. Developing more sensitive detectors and more precise measurement techniques is essential for increasing the chances of successfully detecting dark matter. Moreover, collaboration across various scientific disciplines and technologies is vital. For example, advancements in quantum computing and machine learning could enhance the analysis of experimental data, potentially isolating the subtle signals indicative of dark matter. Financial investment is also a critical factor. Large-scale experiments require significant funding, not only for the construction and maintenance of facilities, but also for long-term data collection and analysis, which are necessary given the rare nature of dark matter interactions. Public and political support is equally important. The search for dark matter often requires a long-term commitment, which can be challenging to sustain without widespread understanding of its importance and potential impact on our understanding of the universe. Theoretical flexibility is another challenge. As experimental efforts continue to refine what dark matter is not, theoretical models must also be adapted. This iterative process between theory and experiment is key to narrowing down the possible characteristics of dark matter. Educational outreach and training. The next generation of scientists and the techniques and challenges of dark matter detection are also crucial. As older hypotheses are tested and new ones are formulated, fresh perspectives and ideas are vital. The search for dark matter also raises philosophical questions about the nature of the universe and our methods of studying it. What does it mean if a significant portion of the universe's mass is something that cannot be directly observed with any traditional methods? Ultimately, detecting dark matter requires persistence, innovation, and a willingness to explore the unknown. Each experiment, whether it results in a detection or not, brings us closer to understanding the true nature of dark matter and, by extension, the universe itself. Dark energy is one of the most profound mysteries in modern cosmology. It refers to an unknown form of energy that is thought to permeate all of space and to accelerate the expansion of the universe. Discovered through observations of distant supernovae in the late 1990s, this acceleration was completely unexpected and has since posed significant challenges to our understanding of the cosmos. The existence of dark energy suggests that the fabric of the universe is not only expanding, but doing so at an increasing rate. This acceleration goes against the previously held notion that the expansion of the universe caused by the Big Bang would gradually slow down due to the gravitational pull of matter. Dark energy constitutes about 68% of the total energy density of the universe. Despite its dominance, it remains invisible and undetectable by traditional means. It does not emit, absorb, or reflect light, and interacts with the visible universe primarily through its gravitational effects. The most widely accepted explanation for dark energy is the cosmological constant, a concept introduced by Albert Einstein as a modification to his general theory of relativity. This constant represents an energy density filling space homogeneously, a property that remains constant over time and space. Another theory proposes that dark energy is dynamic, changing over time and space. This theory introduces the concept of quintessence, a field that varies throughout the universe and affects its expansion rate differently at different times and places. Observations supporting the existence of dark energy come primarily from measurements of the universe's expansion rate using distant supernovae, the large-scale structure of the universe, and fluctuations in the cosmic microwave background radiation. One of the major challenges in understanding dark energy is its extreme weakness. Although it dominates the energy density of the universe, its effects are only noticeable on cosmological scales, making it incredibly difficult to study and quantify using laboratory-based experiments. The implications of dark energy are profound, influencing not only cosmology but also fundamental physics. It challenges our understanding of gravity and the overall dynamics of the universe, suggesting modifications might be needed in Einstein's theory of general relativity. Addressing the mystery of dark energy could lead to new insights into the fate of the universe. Depending on its properties, the universe could continue to expand indefinitely, slow its expansion, or even begin to contract. Researchers are currently employing a variety of methods to probe the nature of dark energy. These include detailed surveys of galaxies and galaxy clusters, studies of the cosmic microwave background, and the use of gravitational lensing to observe the distribution of dark energy. Theoretical physicists are also exploring the possibility that dark energy might be linked to other unsolved problems in physics, such as the nature of dark matter and the unification of quantum mechanics with general relativity. Advanced technologies and new telescopes are crucial in the ongoing quest to understand dark energy. Projects like the Dark Energy Survey and the upcoming Euclid mission by the European Space Agency are designed to map the universe's expansion history and structure more precisely than ever before. Public interest and funding are vital for sustaining research into dark energy. The complexity and scale of experiments needed to explore these questions require substantial, long-term investment. Educational efforts are also important in explaining the significance of dark energy to the broader public. Understanding dark energy is not only about expanding our knowledge of the cosmos, but also about exploring fundamental questions regarding the nature of space and energy. Ultimately, unraveling the mystery of dark energy represents one of the most exciting frontiers in astronomy and physics, promising to reshape our understanding of the universe and potentially leading to new theories that could unlock other mysteries of the cosmos. In the quest to understand the universe, several alternative theories and new research directions have emerged, challenging conventional models and proposing new explanations for the observed phenomena in cosmology. These theories often address the anomalies and discrepancies that arise from traditional frameworks like the lambda cold dark matter model. One prominent alternative theory is modified Newtonian dynamics, or MOND. This theory proposes adjustments to Newton's laws at very low accelerations, such as those found at the outer edges of galaxies, to account for the rotational speeds of galaxies without invoking dark matter. MOND has had some success in explaining certain galactic phenomena, but struggles with larger-scale structures like galaxy clusters. Another approach is the theory of modified gravity, which suggests changes to Einstein's general relativity. These modifications aim to account for the accelerated expansion of the universe and the behavior of galaxies without requiring dark matter or dark energy. Theories like FR gravity and scalar tensor theories fall into this category. String theory, a broader theoretical framework, also provides insights into cosmology. It suggests that the fundamental particles we observe are not point-like dots, but rather small, vibrating strings. String theory has implications for the early universe, potentially explaining inflation and offering a framework for a unified theory of physics. Loop quantum gravity is another significant area of theoretical research that attempts to quantize gravity. It is particularly focused on understanding the fabric of space-time at the Planck scale, which could illuminate early universe conditions and offer insights into the areas where general relativity breaks down, such as inside black holes. The concept of the multiverse has also gained traction as an alternative theory in cosmology. It suggests that our universe might be just one of many universes, each with its own laws of physics. This theory could potentially explain the fine-tuning of certain physical constants in our universe by suggesting that different universes might have different constants. Research in cosmology is also being pushed forward by simulations. Advanced computer models allow researchers to simulate the evolution of the universe under different conditions and with different theoretical assumptions. This helps in understanding the formation of large-scale structures and the effects of dark energy and dark matter. Observational cosmology is experiencing a renaissance with new instruments like the James Webb Space Telescope and the Event Horizon Telescope. These instruments provide higher resolution and more sensitive measurements that can test the predictions of alternative theories more rigorously. Experiments in particle physics, like those conducted at the Large Hadron Collider, also intersect with cosmological research. These experiments can potentially discover new particles that might make up dark matter or provide evidence for theories like supersymmetry, which is closely related to string theory. Gravitational wave astronomy has opened a new window into the cosmos, allowing the study of phenomena that are invisible in electromagnetic light. This field could provide crucial insights into the early universe and test theories about the fundamental nature of space and time. Machine learning and artificial intelligence are becoming increasingly important in cosmology. These technologies help in sifting through large volumes of data to identify patterns and anomalies that might be signatures of new physical phenomena or evidence supporting alternative theories. Cosmology also benefits from interdisciplinary research, incorporating ideas from quantum mechanics, statistical mechanics, and information theory. This cross-pollination can lead to innovative approaches to solving cosmological puzzles, such as the nature of the cosmic microwave background anomalies. Theoretical physicists are increasingly exploring the implications of entropy and thermodynamics on a cosmic scale. This research could provide deeper insights into the arrow of time and the ultimate fate of the universe. Research in cosmology not only focuses on the large scales of galaxies and clusters, but also on the very small scales of the early universe. Understanding the quantum aspects of the early universe could unveil new physics that bridges the gap between quantum mechanics and cosmology. Finally, as we continue to explore these alternative theories and new research directions, the field of cosmology remains one of the most dynamic areas of science. Each theory not only offers a potential solution to existing problems, but also opens up new questions and possibilities, continually driving the frontiers of our knowledge about the universe. The shape and topology of the universe are fundamental aspects of cosmology, and various theories have been proposed to describe them. These theories aim to answer one of the most profound questions: what is the overall structure of the universe? One of the primary models is the flat universe theory, which suggests that the universe has a zero curvature on a large scale, resembling a flat sheet. This theory aligns with the general predictions of inflationary models and is supported by measurements of the cosmic microwave background radiation. Another theory proposes a closed universe, which posits that the universe has a positive curvature, similar to the surface of a sphere. This model implies that if you travel far enough in one direction, you would eventually return to your starting point, and the universe would be finite but without boundaries. Conversely, an open universe theory suggests that the universe has a negative curvature, akin to a saddle shape. This model implies that the universe will expand forever at an ever-increasing rate, and it is infinite in extent. The topology of the universe can also be more complex than simple geometric models. Some theories suggest a multi-connected universe, where space is multiply-connected at different scales. This could mean that the universe has a more intricate shape that could allow for paths that loop back on themselves in unusual ways. Another intriguing idea is the toroidal universe, which proposes that the universe has a donut-shaped topology. This theory allows for an interesting property where traveling in a straight line in certain directions could eventually lead you back to your starting point. The Poincaré dodecahedral space theory suggests that the universe could be shaped like a dodecahedron, a 12-faced polyhedron. This model is motivated by some observations of the cosmic microwave background that hint at a certain pattern of repetition in the sky. Some cosmologists explore the possibility that the universe could have a fractal structure, where the distribution of matter on large scales repeats itself at smaller scales. This model challenges the conventional view of a uniform and isotropic universe as seen in the cosmic microwave background. Quantum cosmology introduces concepts where the shape of the universe is linked to quantum processes that occurred in the very early universe. These theories often lead to scenarios where the topology of the universe is subject to quantum fluctuations, leading to a dynamic and possibly changing shape. String theory also provides models for the universe's shape, suggesting that the apparent four-dimensional universe is actually a manifestation of higher dimensional space. In these models, the extra dimensions could be compactified in complex ways that influence the properties of spacetime. In the realm of speculative theories, the holographic principle suggests that all of the information contained within a volume of space can be represented on a boundary to that space. This principle implies a radically different topology of the universe, where our perceptions of volume are merely projections of information encoded on a distant 2D surface. The Eck-Perotic model, derived from string theory, suggests that our three-dimensional universe is one of two branes, separated by a higher dimensional space. The shape of the universe in this theory is heavily influenced by the interactions between these branes. Loop quantum gravity introduces a concept where the topology of the universe is discrete at the smallest scales, composed of tiny loops woven into the fabric of space-time. This theory offers a potential explanation for the granularity of space at the Planck scale. Chaos theory has been applied to cosmology to explore whether small changes in the shape or topology of the early universe could have led to significant differences in the universe's structure on larger scales. This approach studies the sensitivity of the universe's outcome to its initial conditions. The multiverse theory extends the discussion of the universe's shape by suggesting that our universe might be just one bubble in a larger cosmic foam. Each bubble in this foam could have a different shape and set of physical laws. Ultimately, the true shape and topology of the universe remain subjects of intense study and debate. Each theory offers unique insights and predictions, contributing to our evolving understanding of the cosmos. These diverse theories underscore the richness and complexity of cosmological research, as scientists use both observational data and mathematical models to probe the universe's most profound secrets. Observational evidence plays a critical role in cosmology, serving as the backbone for testing theories and refining our understanding of the universe. Each piece of evidence provides crucial insights and has significant implications for our models of the universe. The cosmic microwave background radiation, or CMB, is one of the most significant observations in cosmology. Detected in the mid-20th century, this faint glow left over from the Big Bang provides a snapshot of the universe when it was just 380,000 years old. The uniformity and slight variations in the CMB have been critical in supporting the Big Bang model and studying the early universe's composition and dynamics. Galaxy rotation curves are another pivotal piece of observational evidence. By studying the rotation speeds of galaxies at various distances from their centers, astronomers have inferred the presence of dark matter. The curves suggest that there is far more mass present within galaxies than can be accounted for by visible matter alone. Gravitational lensing is a phenomenon that occurs when the gravity of a massive object bends the path of light passing near it. This effect has been used to map the distribution of dark matter in the universe, as the light from distant galaxies is bent by intervening dark matter, revealing its presence even though it cannot be seen directly. The accelerating expansion of the universe was discovered through observations of distant Type Ia supernovae. These observations showed that supernovae were dimmer than expected, implying that they were farther away than previously thought, leading to the conclusion that the universe's expansion is accelerating under the influence of dark energy. The large-scale structure of the universe, observed through massive surveys of galaxies, reveals a web-like structure composed of galaxy clusters, filaments, and voids. This structure has been instrumental in developing and testing models of cosmic evolution and the role of dark matter in shaping the universe. Redshift surveys have measured the redshift of galaxies to create a three-dimensional map of the universe over significant volumes. These surveys provide evidence for the scale of the universe's expansion and serve as a tool for understanding the distribution of galaxies and their evolution over time. The detection of the baryon acoustic oscillations provides a standard ruler for measuring the universe's expansion. These oscillations are preserved in the distribution of galaxies and offer a method to measure the scale of cosmic structures independently of supernovae and the CMB. Observations of the oldest stars and galactic formations provide limits on the age of the universe. By determining the age of the oldest stellar populations, astronomers can test predictions of cosmic evolution and the timing of key events in the history of the universe. The recent detection of gravitational waves has opened a new window into the cosmos. These ripples in space-time caused by cataclysmic events, such as black hole mergers, provide a direct way to test theories of gravity and study objects and phenomena that are otherwise invisible. Radio astronomy has revealed details about the universe's magnetic fields and the role of energetic particles and processes. Studies of radio emissions from galaxies and other cosmic sources help fill in gaps about the universe's electromagnetic environment and dynamics. The study of cosmic rays, high-energy particles that strike the Earth's atmosphere, offers insights into the processes occurring in the most energetic environments in the universe. Observations of cosmic rays can hint at the origins of these particles and the nature of high-energy astrophysical events. Spectral analysis of celestial bodies helps in understanding the chemical composition and physical conditions of stars and galaxies. By splitting light into its component wavelengths, astronomers can infer the presence of elements and compounds, revealing the processes that govern star formation and evolution. Infrared astronomy has penetrated dust clouds that obscure visible light, allowing the observation of star birth in molecular clouds and the centers of galaxies, providing insights into processes hidden from optical telescopes. Ultraviolet astronomy explores higher energy processes not observable from the ground due to the Earth's atmosphere blocking most ultraviolet light. Observations in this band have revealed details about the hottest stars and the intergalactic medium. Each piece of observational evidence not only supports or challenges existing theories, but also raises new questions, driving the continuous evolution of cosmological science. Through these observations, cosmologists piece together the history and structure of the cosmos, progressively unveiling the universe's most profound secrets. The field of cosmology is rife with theoretical challenges and open questions, each driving the frontier of scientific inquiry and deepening our understanding of the universe. These challenges often revolve around reconciling observed phenomena with established theories, or extending those theories to explain new data. One of the primary theoretical challenges in cosmology is the nature of dark matter. Although dark matter is a cornerstone of the current cosmological models, explaining the gravitational effects in galaxy rotation and clustering, its exact composition remains unknown. Identifying what dark matter is made of continues to elude scientists. Another significant challenge is understanding dark energy and its role in accelerating the expansion of the universe. The cosmological constant, introduced by Einstein and later associated with dark energy, fits within the mathematical framework of general relativity, but does not offer a dynamic explanation for how or why dark energy changes over time, if at all. The integration of quantum mechanics and general relativity remains one of the greatest theoretical hurdles. These foundational pillars of physics govern the very small and the very large, respectively, but they do not seamlessly integrate. A theory of quantum gravity that could unify these domains is a major goal in theoretical physics. The inflationary model of the early universe, proposing a rapid expansion shortly after the Big Bang, explains the uniformity of the cosmic microwave background and the distribution of galaxies. However, what exactly triggered inflation and what ended it are questions that still need definitive answers. The possible existence of a multiverse introduces substantial theoretical and philosophical challenges. If multiple universes exist, each potentially with its own set of physical laws, how can we begin to study or even prove the existence of these separate realms? The fine-tuning problem questions why the constants of nature are precisely set to allow for the existence of life. Is our universe uniquely suited for life by chance, necessity, or some anthropic principle that necessitates further philosophical and scientific exploration? The problem of initial conditions in the universe also poses significant theoretical challenges. Why did the Big Bang happen with the specific properties and parameters observed? This question touches on the boundary between physics and metaphysical inquiry, challenging our understanding of causality and existence. The reconciliation of observed anomalies in the cosmic microwave background radiation with the standard model of cosmology is another area of active research. These anomalies could be statistical flukes or signs of new physics that need to be integrated into cosmological models. The mystery of baryon asymmetry, the observed imbalance between matter and antimatter in the universe, challenges theoretical physics to find a mechanism that could explain this disparity. Without such a mechanism, the universe as we know it, predominated by matter, cannot be satisfactorily explained. The future fate of the universe is an open question, tied deeply to the properties of dark energy. If dark energy remains constant, the universe could continue expanding forever. But if it changes, the universe could eventually collapse or reach some other dramatic conclusion. Understanding the smallest scales of the universe and how they influenced its early development is another challenge. Quantum fluctuations during the Big Bang are believed to have led to the large-scale structure of the universe observed today, but connecting these quantum beginnings to the cosmological outcomes remains a difficult task. The role of black holes, especially supermassive black holes at the centers of galaxies, in cosmic evolution is not fully understood. These massive objects influence their surroundings in profound ways, but their ultimate impact on galaxy formation and evolution is still being studied. The formation of galaxies and the exact processes by which matter initially coalesced to form stars and galaxies are still not completely understood. The interplay of dark matter, gas dynamics, and gravity in these processes presents a complex puzzle. The challenge of simulating the universe with sufficient accuracy to test cosmological theories against observations requires massive computational power and sophisticated understanding of physics at all scales, from the quantum to the cosmic. Each of these theoretical challenges and open questions not only underscores the complexity of the universe, but also highlights the dynamic nature of cosmology as a field constantly pushing the boundaries of human knowledge. As these questions are explored, they pave the way for new paradigms and deeper insights into the cosmos. General relativity, formulated by Albert Einstein in 1915, is a theory of gravitation that describes gravity not as a force between masses, as Isaac Newton's theory suggested, but as a curvature of space-time caused by mass and energy. According to general relativity, the presence of matter changes the geometry of space-time, and this curvature dictates how matter moves and how light propagates. Quantum mechanics, developed in the early 20th century, deals with physics at very small scales, where particles and waves exhibit behaviors that do not conform to classical physics. The core principle of quantum mechanics is the wave-particle duality, which suggests that every particle or quantic entity may exhibit properties of both particles and waves. It introduces the concept of quantum states, which are described by wave functions that encode the probabilities of all possible positions, energies, and other properties of a particle. One of the fundamental aspects of general relativity is its reliance on the metric tensor, a mathematical construct that describes the curvature of space-time in the vicinity of mass and energy. The equations of general relativity, known as the Einstein field equations, relate this tensor to the energy-momentum tensor that characterizes the density and flux of energy and momentum in space-time. Quantum mechanics also introduces the uncertainty principle, formulated by Werner Heisenberg, which states that certain pairs of properties, like position and momentum, cannot both be precisely measured at the same time. The more precisely one property is measured, the less precisely the other can be controlled or determined. Another principle of general relativity is the equivalence principle, which posits that the gravitational mass, which determines the strength of a gravitational field, and the inertial mass, which determines the resistance to motion in response to a force, are equivalent. This principle is exemplified by the observation that all objects fall at the same rate in a gravitational field, regardless of their mass. In quantum mechanics, the principle of superposition states that a physical system exists, partly in all its theoretically possible states, simultaneously. However, when measured, it gives results corresponding to one of the possible configurations. This principle is famously illustrated by the thought experiment known as Schrödinger's cat. General relativity is a deterministic theory, where the equations predict a single, unique future given initial conditions. The evolution of the universe and the motion of objects within it are absolutely determined by their initial states and the laws of physics. Contrastingly, quantum mechanics is fundamentally probabilistic, meaning that it predicts the probability distributions of outcomes rather than definite outcomes. This aspect of quantum mechanics reveals a fundamental randomness in the processes that occur at the smallest scales of nature. The theory of general relativity also implies the existence of phenomena such as black holes, regions of space, where the space-time curvature becomes so intense that not even light can escape from them. It also predicts gravitational waves, ripples in the curvature of space-time that propagate through the universe at the speed of light. Quantum mechanics, for its part, introduces the concept of quantum entanglement, a physical phenomenon that occurs when pairs or groups of particles are generated, interact, or share spatial proximity in ways such that the quantum state of each particle cannot be described independently of the state of the others, even if the particles are separated by a large distance. The unification of general relativity and quantum mechanics remains one of the most significant challenges in modern physics. The two theories operate on very different scales and under very different conditions, and attempts to reconcile them in a single theoretical framework have led to the development of theories such as string theory and loop quantum gravity. General relativity's description of gravity as the effect of space-time curvature is crucial for understanding large-scale phenomena, such as the orbits of planets, the dynamics of galaxies, and the evolution of the universe itself. Meanwhile, quantum mechanics is essential for describing the interactions and properties of atoms and subatomic particles, explaining the structure of atoms, the nature of chemical bonds, and the properties of condensed matter. Both theories have been extensively tested and have numerous applications. General relativity is critical in the field of astrophysics and is essential for the accurate placement of satellites and the GPS technology that relies on them. Quantum mechanics has led to the development of most modern technology, including computers, lasers, and nuclear power. Understanding and potentially unifying these core principles remains at the forefront of theoretical physics, promising not only deeper insights into the nature of reality, but also paving the way for future technological advancements. General relativity and quantum mechanics are two pillars of modern physics, each highly successful in its domain. However, they are fundamentally incompatible with each other when it comes to describing the universe under extreme conditions, such as near black holes or during the very early moments of the Big Bang. General relativity, Albert Einstein's theory, provides a description of gravity as a geometric property of space and time, or spacetime. It explains how mass and energy dictate the curvature of spacetime, which in turn controls the motion of masses. This theory works exceptionally well at large scales and has been confirmed by many experiments and observations, such as the bending of light by gravity and the detection of gravitational waves. Quantum mechanics, on the other hand, deals with the smallest scales of energy levels of atoms and subatomic particles. It introduces concepts like wave-particle duality, where particles exhibit both particle-like and wave-like properties, and the uncertainty principle, which states that certain pairs of properties, like position and momentum, cannot be simultaneously known to arbitrary precision. The incompatibility arises because general relativity is a classical theory where things have definite properties and states determined by deterministic laws that predict specific outcomes. Quantum mechanics, however, is inherently probabilistic, predicting probabilities of different outcomes rather than definite ones. One of the main issues is that general relativity predicts that space and time are smooth and continuous, while quantum mechanics suggests that at the smallest scales, they should be discrete and quantized. This leads to conceptual and mathematical difficulties when trying to describe the gravitational field in quantum terms. When trying to apply quantum mechanics to the gravitational field, calculations often result in what are known as infinities, which are nonsensical from a physical point of view. These infinities appear because of the way quantum field theories handle extremely high energies and short distances, something that is commonplace in the realms where both gravity and quantum effects are strong. Another example of their clash is the issue of time. In quantum mechanics, time is a background parameter, a fixed and unchanging stage on which particles move. However, in general relativity, time is dynamic and is influenced by gravity and can vary in different parts of the universe. Additionally, in scenarios like the singularity at the center of a black hole, general relativity predicts a point where density becomes infinite and space-time curvature becomes infinite. Quantum mechanics, fundamentally based on the uncertainty principle, denies the existence of such singular points with precisely defined locations. Moreover, quantum mechanics requires a fixed space-time background to define the particle's properties, but general relativity declares that space-time itself is dynamic and shaped by energy and matter, leading to a fundamental conflict about the nature of space-time itself. This incompatibility suggests that at least one of the theories is incomplete. It points to the need for a theory of quantum gravity that can seamlessly merge these two foundational theories into a single framework that works across all scales and energies. Attempts to develop a unified theory include string theory, which posits that the point-like particles of particle physics are actually one-dimensional strings, and loop quantum gravity, which tries to quantize space-time itself. The incompatibility of these two theories is one of the most profound and fundamental issues in theoretical physics. It not only challenges our understanding of the universe, but also drives much of the research in cosmology and particle physics. Resolving this issue is crucial for progressing towards a complete and unified description of the fundamental forces of nature, potentially leading to insights into the early universe, black holes, and maybe even the ultimate fate of the cosmos. In practical terms, until a unified theory is developed, scientists must choose whether to use quantum mechanics or general relativity depending on the situation. For most everyday applications involving gravity on Earth or in the solar system, general relativity suffices, while for dealing with atoms and particles, quantum mechanics is used. The quest to bridge the gap between quantum mechanics and general relativity continues to be a central pursuit in theoretical physics, inspiring new ideas, technologies, and experiments designed to probe the foundations of the universe. Developing a theory of quantum gravity is among the most significant challenges in modern theoretical physics. It involves bridging the gap between general relativity, which describes the macroscopic world, and quantum mechanics, which governs the microscopic. The quest for such a theory is not only motivated by the desire for a deeper understanding of the universe, but also to resolve the fundamental incompatibilities between these two pillars of physics. One of the primary efforts in this direction is string theory, which posits that particles are not zero-dimensional points, but rather one-dimensional strings. These strings vibrate at different frequencies, and their vibrations correspond to different particles. String theory is appealing because it provides a framework that includes gravity and could unify all fundamental forces of nature under one umbrella. Loop quantum gravity, LQG, is another significant approach, which attempts to quantize space itself. It suggests that space is not continuous but made up of tiny loops woven into a fabric. This theory directly tackles the problem of singularity and infinite density, predicted by general relativity in black holes and the Big Bang. A major challenge in developing a theory of quantum gravity is the lack of experimental evidence. Quantum effects of gravity are expected to become significant only at the Planck scale, which is about 10 to 35 meters, far beyond the reach of current or foreseeable experimental technology. This makes it difficult to test predictions and refine theories based on empirical data. Moreover, both string theory and loop quantum gravity require complex mathematics and lead to scenarios and predictions that are not only difficult to test, but also hard to relate to observable physics. For instance, extra dimensions posited by string theory are not directly observable, and the granular structure of space suggested by LQG has not yet found empirical support. Theoretical physicists also face the challenge of ensuring that any proposed theory of quantum gravity reduces to general relativity in the macroscopic limit and to quantum mechanics in the microscopic limit. This requirement is known as the correspondence principle and ensures that the new theory respects what is already known and tested. Another effort in this field is the exploration of black holes and their properties, as they are where the effects of quantum mechanics and general relativity converge. The information paradox, which involves the fate of information that falls into a black hole, is a problem that any successful theory of quantum gravity must address. Gravitational wave astronomy offers a new potential window into testing theories of quantum gravity. Detecting the quantum aspects of gravitational waves could provide clues about the quantum nature of space-time itself, offering a novel way to gather empirical data relevant to quantum gravity theories. The development of a theory of quantum gravity also has philosophical implications, challenging our understanding of reality, causality, and the nature of space and time. These conceptual issues must be addressed alongside the mathematical and experimental challenges. Many theorists believe that developing a theory of quantum gravity may require new mathematical tools and concepts that do not yet exist. The complexity of merging such fundamentally different theories might necessitate a revolution in mathematical physics. The holographic principle, derived from string theory, suggests that all of the information contained within a volume of space can be represented on the boundary of that space. This principle has inspired new approaches to quantum gravity that treat the bulk of space-time and its boundary as two manifestations of the same physical reality. The cosmological constant problem, which arises from the discrepancy between the calculated and observed values of dark energy, poses another theoretical challenge. A theory of quantum gravity might provide a framework for understanding why the cosmological constant is so small, which remains one of the biggest mysteries in physics. Some physicists are exploring the possibility that quantum gravity could emerge from a more fundamental theory that does not primarily focus on gravity, but rather derives it as an emergent phenomenon from deeper quantum mechanical principles. A theory of quantum gravity may also illuminate the conditions of the universe at the very moment of the Big Bang, providing a clearer picture of how the universe began and evolved, and possibly explaining what came before it. Lastly, the endeavor to unify all known forces under a single theory, including gravity, continues to drive fundamental research in physics. It's a pursuit that not only stretches our imagination and technical capabilities, but also deepens our understanding of the universe. These efforts and challenges underscore the complexities and profound nature of seeking a theory of quantum gravity. It is a pursuit that bridges the deepest understandings of the cosmos, from the minuscule particles to the expansive dance of galaxies, all bound by the quest to understand the fabric of reality itself. Modified Newtonian dynamics, or MOND, is an alternative theory to Newtonian gravity and general relativity, particularly focused on explaining the dynamics of galaxies without invoking dark matter. MOND proposes a modification of Newton's second law of motion at very low accelerations, typical of the outer regions of galaxies. According to MOND, the gravitational force experienced by a star on the outskirts of a galaxy does not follow the inverse square law, but rather increases more than Newtonian predictions, providing the necessary force to explain the observed flat rotation curves of galaxies without the need for dark matter. TVES, or tensor vector scalar theory, is an extension of MOND that was formulated to incorporate MOND-like behavior into a relativistic gravitational theory. Developed by Jacob Bekenstein, TVES adds vector and scalar fields to the tensor field of general relativity. This theory aims to provide a framework not only for explaining galaxy dynamics, but also for achieving consistency with cosmological phenomena, such as gravitational lensing and the cosmic microwave background, under a unified theory without dark matter. FR. Gravity is a type of modified gravity theory that extends general relativity by modifying the Lagrangian of the theory to be a function of the Ricci scalar r, instead of just being proportional to r. FR theories introduce modifications to the gravitational action, which can lead to different predictions at cosmic scales. These modifications are designed to explain the accelerated expansion of the universe without the need for dark energy, and also to provide alternative explanations for other cosmological and astrophysical phenomena. MOND and its relativistic generalization, TVES, challenge the dark matter paradigm by suggesting that the anomalies observed in galactic rotation curves can be accounted for by changes to the laws of gravity rather than by the presence of unseen matter. These theories have sparked significant debate and research, particularly in the context of explaining the detailed dynamics of individual galaxies. However, MOND faces difficulties at larger scales, such as in clusters of galaxies where additional unseen mass seems necessary, even under MOND's modified dynamics. This has led some researchers to consider hybrid models that incorporate both modifications to gravity and some form of dark matter. TVES, while it resolves some of the issues with MOND at cosmological scales, has been critiqued for its complexity and the introduction of additional fields whose physical nature is not well understood. Despite these criticisms, TVES remains a significant step in the development of coherent alternatives to dark matter. FR. Gravity models have been extensively studied for their cosmological implications. These models are particularly appealing because they can mimic the cosmological constant at large scales and modify the growth of structure in the universe, potentially leading to observable signatures that differ from predictions of general relativity plus dark matter. One of the appealing aspects of FR gravity is its mathematical beauty and simplicity in some forms. By simply changing the functional form of FR, one can generate a wide variety of cosmological behaviors, providing a rich framework for explaining cosmological observations, with fewer assumptions about the contents of the universe. The testing of these theories involves precise astronomical observations. For MOND and TVES, observations of the motion of stars and gas in galaxies, as well as gravitational lensing data, are crucial. For FR gravity, cosmological observations such as the cosmic microwave background, large-scale structure, and high redshift supernovae are key. Despite their potential, none of these theories have yet provided a complete and universally accepted solution to the problems they aim to solve. Each has its strengths and successfully explains certain observational phenomena, but also faces challenges and anomalies that require further theoretical development and more data. Debate and research into MOND, TVS, and FR gravity are active areas in theoretical physics and astronomy. They represent a broader quest within the scientific community to explore alternatives to the standard cosmological model, which is dominated by dark matter and dark energy. These theories highlight the importance of keeping an open mind in scientific inquiry. As more data becomes available and our theoretical and computational tools improve, these alternative theories are continually refined and either gain support or are ruled out. The exploration of these alternatives is not just academic. It has profound implications for our understanding of the universe. They challenge the conventional components of the cosmos and offer new ways of thinking about gravity and the dynamics of the universe. In conclusion, MOND, TVS, and FR gravity are important components of the ongoing discussion and investigation into the fundamental forces that shape the cosmos. Whether any of these theories will eventually supplant or significantly modify the current consensus on dark matter and dark energy remains to be seen. Ultimately, the value of investigating these theories lies not only in what they can explain, but also in the new questions they raise and the new research directions they inspire, contributing to the dynamic and evolving nature of cosmological science. Theoretical motivations for exploring alternative theories of gravity are rooted in the unresolved issues within general relativity and cosmology, particularly the mysteries surrounding dark matter and dark energy. Scientists propose modifications to our current understanding of gravity to see if these can explain cosmological observations without the need for unseen mysterious substances. One significant motivation is the inability of the lambda cold dark matter model to explain certain astronomical observations without postulating the existence of dark matter and dark energy. These components, which make up about 95% of the universe's total energy density, have not been directly detected, prompting theories that modify gravity instead. Another theoretical motivation comes from the problem of galaxy rotation curves, which do not match the predictions made by Newtonian gravity unless additional mass, assumed to be dark matter, is included. Alternative theories of gravity, such as modified Newtonian dynamics, MOND, attempt to explain these curves through changes to the laws of gravity, rather than invisible mass. The accelerated expansion of the universe observed through measurements of distant supernovae is another motivator. It suggests that some form of repulsive energy, termed dark energy, is driving this expansion. Alternative gravity theories like FR gravity explore whether modifications to Einstein's field equations could account for this acceleration without the need for dark energy. Theoretical motivations also stem from the desire for a more unified physics. Modifications to gravity are often explored in the context of achieving a theory that can reconcile quantum mechanics with general relativity, potentially leading to insights into quantum gravity. From an observational standpoint, constraints are crucial in testing the viability of these theories. One major constraint comes from the precise measurements of the cosmic microwave background radiation, which offers detailed insights into the early universe's conditions and strongly supports the standard cosmological model. Gravitational lensing observations provide another critical test. The bending of light by massive objects like galaxies and galaxy clusters must be accounted for by any viable theory of gravity. Discrepancies in lensing data can often rule out or constrain alternative gravity models that do not require dark matter. The large-scale structure of the universe, observed through galaxy surveys, also imposes constraints. The distribution of galaxies and their clustering properties can indicate how gravity operates on large scales, providing a way to test different gravitational theories against the standard model. Solar system tests are particularly stringent constraints for modified gravity theories. Any new theory must reduce to Newtonian gravity under the conditions present in our solar system, where general relativity has been confirmed to high precision through observations like the precession of Mercury's orbit and the deflection of light by the Sun. Binary pulsar systems, which provide a natural laboratory for testing general relativity, also serve as observational constraints. The energy loss through gravitational waves observed in these systems matches the predictions of general relativity very closely, setting a high bar for any alternative theory. The behavior of neutron stars and black holes, particularly as observed through gravitational wave astronomy, offers new ways to constrain theories. The merger rates, mass distributions, and waveform signals from these events must all be consistent with observed data, which can be challenging for some modified gravity theories. In cosmology, the age of the universe derived from different measurements provides a cross-check against theoretical predictions. Any modified theory of gravity must account for the observed expansion history and age of the universe, consistent with measurements from the cosmic microwave background, supernova, and other astrophysical clocks. Observations of the early universe's thermal history and nucleosynthesis also impose constraints. Theories of gravity that alter the dynamics of the early universe must still allow for the correct abundance of light elements such as helium and lithium, as predicted by Big Bang nucleosynthesis. The integrated Sachs-Wolf effect, where photons from the cosmic microwave background gain energy, passing through potential wells caused by large-scale structures, provides another observational test. Discrepancies in this effect could hint at different gravitational behaviors predicted by alternative theories. Ultimately, the interplay between theoretical motivations and observational constraints shapes the development of alternative theories of gravity. Each observation acts as a puzzle piece, and any new theory must fit together with existing pieces to provide a coherent and empirically supported picture of the universe. These efforts not only challenge our current understanding, but also drive the fundamental quest for a deeper and more comprehensive theory of gravity. The concept of the multiverse suggests that our universe might be just one of many universes, each potentially governed by different physical laws and constants. This idea emerges from various areas of theoretical physics, including cosmological inflation theories and string theory, proposing a vast landscape of possible universes. Inflationary theory, which posits a rapid expansion of the early universe, provides one foundation for the multiverse concept. According to this theory, different regions of space could cease inflating at different times, leading to a bubble of space-time that could function as a separate universe with its own physical laws and constants. String theory further supports the multiverse concept through its landscape of solutions. It suggests a vast number of possible states for the universe, each corresponding to different ways the extra dimensions proposed by the theory could be compactified. Each unique state could theoretically represent a different universe within a broader multiverse. The multiverse concept challenges the traditional cosmological notion that the observable universe is all there is. If our universe is just one of many, this might explain why certain physical constants appear finely tuned for the emergence of life, a question that has puzzled scientists for decades. From a philosophical perspective, the multiverse raises questions about the nature of reality and our place within it. It suggests that our universe might not be as special or unique as we once thought, instead being one of a vast number of universes in a much larger cosmos. Scientifically, the multiverse theory is controversial because it is difficult, if not impossible, to test directly. Since we cannot observe these other universes, the theory remains speculative and largely based on inferences from theoretical physics rather than empirical data. One of the major implications of the multiverse for cosmology is the issue of predictability. If physical laws can vary from one universe to another, this could undermine the idea that there are universal laws of physics that apply everywhere and always. The multiverse also has implications for the notion of initial conditions in cosmology. If each universe within the multiverse can have different initial conditions, the fine-tuning of conditions necessary for life in our universe might not be as improbable as once thought, with many universes existing where such conditions never occur. Anthropic reasoning, which has been used to explain the fine-tuning of physical constants in our universe, gains a new context with the multiverse. This reasoning posits that we observe these conditions simply because we could not exist in a universe where these conditions were not met. Some theorists propose that collisions between these universe bubbles could leave observable imprints in the cosmic microwave background radiation of our universe. offering a potential way to gather evidence for the existence of other universes. The study of black holes has also been connected to the multiverse concept. Some theories suggest that each black hole could give rise to a new universe, potentially different from the parent universe, further expanding the scope of the multiverse. The concept of the multiverse pushes the boundaries of cosmology into the realm of metaphysics, as it deals with entities, other universes, that we may never be able to observe or interact with directly. This raises significant questions about the criteria for scientific theories, particularly about the requirement for empirical testability. In the context of quantum mechanics, the multiverse finds a place in the many worlds interpretation, which posits that all possible outcomes of quantum measurements are physically realized in separate, non-communicating branches of the multiverse. This interpretation eliminates randomness from quantum theory by having all outcomes occur but in different worlds. Despite the challenges in proving the multiverse theory, it remains a vibrant area of theoretical research. It inspires new ways of thinking about fundamental questions in cosmology and the nature of scientific theories, potentially leading to new discoveries about the universe. Ultimately, whether the multiverse theory can move from a speculative idea to a testable scientific framework will depend on the development of new theories and technologies that can infer the presence of other universes or simulate conditions that reflect multiverse dynamics. The exploration of the multiverse continues to stimulate debate across various disciplines, reflecting its profound implications for understanding the cosmos. String theory is a compelling candidate for a unified theory of the fundamental forces of nature, offering a framework that attempts to reconcile quantum mechanics with general relativity. This theory emerged in the late 20th century as a potential theory of everything that could explain all particles and fundamental interactions through the dynamics of tiny, vibrating strings. The core idea of string theory is that the point-like particles of particle physics are not zero-dimensional points, but rather one-dimensional strings. These strings can be open or closed loops, and their vibrations at different frequencies represent different particles. The mass and charge of a particle depend on how the string vibrates, much like different musical notes emerge from different vibrations of guitar strings. String theory is unique in its ability to integrate gravity into the quantum framework, proposing that gravitons, hypothetical quantum particles that mediate gravitational forces, arise naturally within the theory as modes of string vibration. This integration addresses one of the major challenges in theoretical physics, formulating a quantum theory of gravity. One of the striking features of string theory is its requirement of extra dimensions. While our familiar universe has 3 spatial dimensions and 1 time dimension, string theory posits that there are additional hidden dimensions that are compactified at scales too small to be detected with current technology. These extra dimensions are crucial for the mathematical consistency of the theory. String theory also introduces the concept of supersymmetry, a proposed symmetry between the 2 basic classes of particles: bosons, which carry forces, and fermions, which make up matter. Supersymmetry suggests that each particle has a superpartner with similar properties, but differing by half a unit of spin. This symmetry helps to resolve several theoretical problems, including the hierarchy problem related to the mass of the Higgs boson. Another important aspect of string theory is its potential to explain the fine structure of black holes. By viewing black holes not as points, but as states of highly excited strings, string theory offers explanations for their entropy and temperature that align with the laws of thermodynamics, resolving some paradoxes that arise in black hole physics as described by general relativity. String theory also proposes the existence of branes, multidimensional objects on which strings can end. Branes can have dimensions ranging from 0, a point, to 9, filling space, and they introduce new ways of understanding the interactions between particles and forces, potentially explaining why gravity is weaker than the other fundamental forces. In the cosmological context, string theory is attractive because it can potentially provide a quantum description of the early universe. It offers mechanisms for cosmic inflation and alternatives to the Big Bang singularity, suggesting that the universe might have originated from the collision of higher dimensional branes. Despite its beauty and depth, string theory faces significant challenges. One of the biggest is the lack of direct experimental evidence. The energy scales at which string effects would become noticeable are far beyond the reach of current particle accelerators. making experimental verification extremely difficult. Moreover, string theory has a vast number of possible solutions, each corresponding to different ways the extra dimensions can be compactified. This landscape of solutions is both a feature and a bug. It allows for great flexibility in fitting the theory to our universe, but makes it difficult to make definitive predictions. Critics of string theory also point out that it has not yet provided a clear, testable prediction that would allow it to be empirically verified or falsified. This has led to debates within the physics community about the scientific validity of string theory as a physical theory rather than just a mathematical framework. Despite these challenges, string theory continues to be developed and explored because of its potential to unify all the fundamental forces under a single theoretical umbrella. It has also enriched theoretical physics by providing new tools and concepts that have applications across multiple fields of research. Researchers continue to explore string theory, not only to uncover the fundamental nature of particles and forces, but also to apply its mathematical techniques to solve complex problems in quantum field theory, nuclear physics, and early universe cosmology. As string theory develops, it may evolve in ways that bring it into closer alignment with empirical data, or it may serve as a stepping stone to another, more fundamental theory. In either case, it remains one of the most intriguing and rich areas of modern theoretical physics. Exploring string theory is thus a journey at the cutting edge of our understanding of the universe, promising to reshape not only our knowledge of the fundamental particles and forces, but also our broader understanding of the cosmos. The pursuit of theories such as string theory, the multiverse, and other advanced theoretical frameworks presents several significant challenges and has attracted various criticisms. These challenges primarily revolve around the theory's testability, complexity, and their implications for the philosophy of science. One of the primary criticisms of string theory is its current lack of testable predictions. Because string theory operates at energy scales far beyond what current particle accelerators can reach, it has been difficult to devise experiments that can definitively support or refute the theory. This leads to concerns about whether string theory can be considered a scientific theory in the traditional sense, if it cannot be empirically verified. The multiverse theory similarly faces the challenge of testability. By its very nature, the multiverse suggests the existence of other universes that are not causally connected to ours and therefore cannot be directly observed. This raises questions about the scientific validity of the multiverse concept and whether it falls more into the realm of philosophical speculation rather than empirical science. Another criticism of these theories is their mathematical complexity and the heavy reliance on advanced mathematics that can be opaque, even to specialists within physics. This complexity can make the theories less accessible and challenging to communicate, potentially isolating them from broader scientific scrutiny. Critics also argue that the flexibility of theories like string theory, its ability to accommodate almost any observation or experimental result due to the vast landscape of solutions, could be seen as a weakness rather than a strength. This flexibility might allow the theory to explain anything post hoc, thereby reducing its falsifiability. There is also a philosophical criticism regarding the naturalness and elegance of these theories. Some scientists are concerned that the introduction of multiple dimensions, exotic particles, and complex mathematical structures might be an indication of moving away from, rather than toward, a fundamental understanding of nature. The multiverse theory raises profound philosophical questions about the nature of reality and our ability to understand the universe. It challenges the Copernican principle, suggesting that our universe might be special or finely tuned among a vast array of possible universes. Financial and resource allocation is another area of contention. Some in the scientific community argue that the considerable resources devoted to pursuing these high-theory areas could be better spent on more empirically grounded sciences that promise more immediate returns in terms of knowledge and technology. The concept of beauty as a guide in theoretical physics has also been questioned. The pursuit of elegant mathematical equations and aesthetically pleasing theories might lead researchers away from other viable explanations of the universe that are less mathematically elegant, but more aligned with observational data. Critics of the multiverse also argue that it undermines the principle of parsimony or Occam's razor, the idea that the simplest explanation, usually requiring the fewest assumptions, is preferred. The multiverse theory introduces an almost infinite number of universes to explain phenomena in our own universe, which some see as an extravagant assumption. In the case of string theory, there's a challenge in the theory's requirement for supersymmetry. Although supersymmetry makes string theory mathematically coherent, experimental searches for supersymmetric particles have so far come up empty, raising doubts about this foundational aspect of the theory. Moreover, the educational challenge in these fields is significant. Teaching these advanced concepts requires a background in high-level mathematics and physics, making it difficult to integrate them into standard curricula and to engage a wider audience in their discussion and development. Environmental and ethical considerations also come into play, particularly in relation to large-scale experiments that may be required to test aspects of these theories. The construction and operation of massive particle accelerators have environmental impacts and ethical implications that must be considered. Historically, there's a criticism regarding the cyclical nature of theoretical physics, where theories often come back to similar problems and solutions, suggesting a possible stagnation or lack of breakthroughs that fundamentally shift the paradigm. There is also a sociological aspect to the criticism. The small, tightly knit communities of theoretical physicists working on these advanced concepts can sometimes lead to echo chambers where critical scrutiny is minimized and consensus on unproven ideas may be prematurely reached. Lastly, there is a call within the scientific community for a diversification of ideas and approaches. Some suggest that alternative theoretical frameworks might be sidelined due to the dominant focus on popular theories like string theory and the multiverse, potentially ignoring other less mainstream but possibly fruitful avenues of research. The James Webb Space Telescope, JWST, represents a significant advancement in astronomical technology and is designed to be the premier observatory of the next decade. Operating from an orbit about 1.5 million kilometers from Earth, JWST will explore every phase of cosmic history, from within our solar system to the most distant observable galaxies in the early universe, and everything in between. Its capabilities are tailored to observe high redshift star formation, the evolution of galaxies, the production of elements by stars, and the process of planetary formation. The Event Horizon Telescope, EHT, is a remarkable example of global collaboration in the field of astronomy. It is not a single telescope, but a network of radio telescopes around the world, linked together to create a planet-sized interferometer with unprecedented sensitivity and resolution. The EHT is designed to capture images of the immediate environment of supermassive black holes with the highest detail ever achieved, which was demonstrated by the first ever image of a black hole in the galaxy M87. The Hubble Space Telescope, a project of international cooperation between NASA and ESA, has been one of the most versatile and productive telescopes ever built. Since its launch in 1990, Hubble has made more than 1.3 million observations, providing data that astronomers have used to write more than 17,000 peer-reviewed scientific publications on a wide variety of topics, including planetary atmospheres, the expansion rate of the universe, and the age and size of the cosmos. The Very Large Telescope, VLT, operated by the European Southern Observatory on Cerro Paranal in the Atacama Desert of northern Chile, is one of the world's most advanced optical instruments. The VLT consists of 4 individual telescopes, each with a primary mirror 8.2 meters across, which can work independently or together to form a giant interferometer. This allows astronomers to see details up to 25 times finer than with the individual telescopes. The Chandra X-ray Observatory, launched by NASA in 1999, is a satellite that observes X-rays from high-energy regions of the universe, such as the remnants of exploded stars, clusters of galaxies, and matter around black holes. Chandra has helped researchers understand the structure and evolution of the universe, providing insights into the interactions of dark matter and the properties of matter under extreme conditions. The Atacama Large Millimeter-Submillimeter Array, ALMA, located in the harsh conditions of Chile's Atacama Desert, is the most expensive ground-based telescope in operation. ALMA's capabilities allow it to observe light from some of the coldest objects in the universe, with unprecedented sensitivity and resolution, including the formation of stars, planetary systems, galaxies in the early universe, and molecular gas clouds. The Large Synoptic Survey Telescope, LSST, soon to be renamed the Vera C. Rubin Observatory, is currently under construction in Chile and is designed to survey the entire visible sky every few nights. Its wide field of view and rapid scanning capability will produce a wide and deep astronomical data set that will help address some of the most pressing questions about the structure and evolution of the universe, including mysterious dark matter and dark energy. The Keck Observatory, located at the summit of Mauna Kea in Hawaii, consists of 2 telescopes, each 10 meters in diameter. These telescopes are among the largest optical and infrared telescopes available today. Keck Observatory has been a pivotal instrument in many significant discoveries, such as the atmospheric compositions of distant planets and the behaviors of supermassive black holes. The Sloan Digital Sky Survey, SDSS, has been one of the most ambitious and influential surveys in the history of astronomy. Operating out of the Apache Point Observatory in New Mexico, SDSS has created the most detailed three-dimensional maps of the universe ever made, with deep multicolor images of 1/3 of the sky and spectra for more than 3 million astronomical objects. The upcoming Square Kilometre Array, SKA, is set to be the world's largest radio telescope, with eventual sites in South Africa and Australia. By combining signals from thousands of small antennas spread over thousands of kilometers, the SKA will explore cosmic radio waves with unprecedented sensitivity and resolution, examining early universe galaxies, dark energy, and general relativity in extreme conditions. Each of these instruments, with their unique capabilities and technological innovations, plays a critical role in our ongoing exploration of the cosmos. They not only extend our senses into deeper realms of space, but also refine our understanding of the fundamental physics that governs the universe, ensuring continued progress in the field of astronomy and beyond. The James Webb Space Telescope, JWST, addresses cosmological questions by observing the formation of stars and galaxies in the early universe. Its infrared capabilities allow it to look further back in time than ever before, providing insights into the period shortly after the Big Bang when the first galaxies were forming. This helps astronomers understand how the early universe evolved and how the first structures in the universe came into being. The Event Horizon Telescope, EHT, contributes to our understanding of the physics of black holes. By imaging the event horizons of supermassive black holes, the EHT tests predictions of general relativity in extreme conditions. This is crucial for understanding the role of black holes in galaxy formation and evolution, and could potentially reveal new physics by showing deviations from Einstein's theories. The Hubble Space Telescope has been instrumental in determining the rate of the universe's expansion. By observing distant supernovae, Hubble has helped refine measurements of the Hubble constant, a key parameter in cosmology that describes how fast the universe is expanding, shedding light on the dynamics of the cosmos. The Very Large Telescope, VLT, enhances our understanding of dark matter and dark energy by observing the distribution and velocity of galaxies. The VLT's advanced optics allow for detailed observations of the large-scale structure of the universe, which is essential for testing models of cosmic evolution and the large-scale effects of dark energy. The Chandra X-ray Observatory explores the hottest regions of the universe, such as clusters of galaxies and the remnants of supernovae. By mapping the distribution of hot gas in galaxy clusters, Chandra provides evidence for the presence of dark matter, which does not emit light but reveals its presence through its gravitational effects on visible matter. The Atacama Large Millimeter Submillimeter Array, ALMA, observes the cold dust and gas from which stars and planetary systems form. ALMA's high resolution and sensitivity at millimeter and sub-millimeter wavelengths make it an excellent tool for studying the chemical composition and dynamics of these early stages of star and planet formation, providing clues about the conditions under which similar processes might occur in other parts of the universe. The Large Synoptic Survey Telescope, LSST, soon to be operational, will play a key role in addressing cosmological questions related to dark energy and the nature of the cosmic acceleration. By repeatedly surveying large areas of the sky, LSST will track changes over time, helping to map out the expansion history of the universe in unprecedented detail. The Keck Observatory's powerful telescopes allow astronomers to probe the most distant objects in the universe. providing insights into the formation of galaxies at the edge of the observable cosmos. This helps cosmologists test theories about the overall structure of the universe and the evolution of cosmic structures over billions of years. The Sloan Digital Sky Survey, SDSS, has revolutionized our understanding of the universe's large-scale structure. By creating detailed three-dimensional maps of millions of galaxies, SDSS has provided critical data for testing models of galaxy formation and the distribution of dark matter. The Square Kilometre Array, SKA, will address key cosmological questions by mapping the distribution of hydrogen throughout the universe's history. By observing the evolution of hydrogen clouds into galaxies and clusters, SKA will help astronomers understand how the universe's large-scale structures formed under the influence of gravity and dark matter. These instruments collectively address a broad range of cosmological questions, from the properties of the early universe to the behavior of dark matter and dark energy. By observing the universe across different wavelengths and at different times, these tools provide a multifaceted view of the cosmos, enabling a deeper understanding of its most fundamental mysteries. The data gathered by these observatories also test the predictions of theoretical physics, providing a critical feedback loop between observation and theory that is essential for the advancement of cosmological models. Moreover, these instruments help in the search for exoplanets and the analysis of their atmospheres, which contributes indirectly to cosmology by improving our understanding of planetary system formation and the conditions that might lead to habitable environments elsewhere in the universe. By improving our measurement capabilities, these tools also refine the fundamental constants of physics, which are crucial for precise cosmological models. Accurate measurements of these constants allow for better predictions of phenomena such as the cosmic microwave background radiation and the distribution of matter in the universe. In conclusion, the diverse capabilities of these advanced astronomical instruments enable a comprehensive approach to solving the puzzles of the universe. Each tool adds a unique piece to the cosmological puzzle, helping to assemble a coherent picture of how the universe works, from its smallest scales to its largest structures. Innovations in data processing and simulation have become critical in cosmology, enabling scientists to manage and interpret the vast amounts of data collected from astronomical observations and to model complex cosmic phenomena with unprecedented accuracy. One significant innovation has been the development of advanced algorithms for processing the large datasets generated by telescopes, like the Sloan Digital Sky Survey and the upcoming Large Synoptic Survey telescope. These algorithms employ techniques from machine learning and artificial intelligence to automate the classification of galaxies and the detection of astrophysical events, enhancing the speed and accuracy of data analysis. The use of parallel computing architectures is another key innovation. By distributing the processing load across multiple CPUs and GPUs, researchers can handle more complex simulations and larger datasets than would be possible with traditional computing methods. This is particularly important for simulations that involve the dynamics of billions of particles, such as those used in modeling the large-scale structure of the universe. Cloud computing has also transformed data processing in cosmology by providing flexible, scalable computing resources. Scientists can store large volumes of data in the cloud and access vast computing power on demand, facilitating collaboration among international teams and speeding up data analysis and model testing. Simulations of cosmic structures have benefited greatly from improvements in numerical methods, such as n-body simulations, which calculate the gravitational interactions between particles representing dark matter, stars, or galaxies. These simulations have become more realistic by incorporating additional physical processes like gas dynamics, star formation, and feedback from supernovae. The development of synthetic universes through simulations allows cosmologists to test theories of cosmic evolution by comparing simulated data with observational data. This approach helps to refine models of how galaxies form and evolve, and provides insights into the role of dark matter and dark energy in shaping the universe. Data visualization techniques have also seen significant advances, with interactive 3D models and virtual reality environments now being used to explore complex data sets. These tools help scientists and the public to visualize and understand the three-dimensional structure of the universe. Machine learning techniques, including neural networks and decision trees, are being increasingly applied to cosmological data. These methods can identify patterns and correlations in data that are too subtle for traditional analysis techniques, opening new avenues for discovery in large-scale survey data. The integration of Bayesian statistical methods in data analysis allows for better handling of uncertainties and more robust derivation of cosmological parameters. These methods provide a framework for incorporating prior knowledge and making probabilistic inferences about the cosmos. Automated survey telescopes equipped with real-time data processing capabilities can now identify transient astronomical events, such as supernovae and gamma-ray bursts, almost immediately after they occur. This rapid processing enables timely follow-up observations that are crucial for understanding these ephemeral phenomena. Simulations are also being used to explore alternate theories of gravity and to predict their observational signatures. By comparing these predictions with actual observations, cosmologists can constrain or rule out these theories, refining our understanding of the fundamental forces that govern the universe. Quantum computing presents a future avenue for cosmological data processing, with the potential to perform calculations that are infeasible with classical computers. This could revolutionize the simulation of quantum phenomena in the early universe and the processing of massive datasets. The development of autonomous observatory systems, driven by software that can adapt observing strategies in real time based on weather conditions and the data being collected, optimizes the use of telescope time and improves the efficiency of data collection. Enhanced error correction and noise reduction techniques have improved the quality of data obtained from observational instruments. These advancements are crucial for isolating genuine cosmic signals from the noise inherent in measurements taken over vast distances. Lastly, the use of open-source software and collaborative platforms has democratized access to data processing tools and cosmological simulations, fostering a more inclusive global community of researchers. This has led to a more collaborative approach to solving cosmological puzzles, integrating diverse perspectives and expertise. Together, these innovations in data processing and simulation are driving forward our understanding of the universe, enabling cosmologists to tackle more complex questions than ever before and paving the way for new discoveries in the field. Artificial intelligence and machine learning are transforming cosmology by enabling researchers to handle vast amounts of data and complex simulations with unprecedented efficiency and precision. These technologies are particularly useful in areas where the volume and complexity of the data exceed the capabilities of traditional analytical methods. Machine learning algorithms, for instance, are employed to analyze images from telescopes to automatically classify galaxies based on their shapes, sizes, and other properties. This automation speeds up the process of cataloging astronomical objects and allows astronomers to focus on more nuanced analysis and interpretation. Deep learning, a subset of machine learning, is being used to identify subtle patterns in the cosmic microwave background radiation. These patterns can provide insights into the early universe's conditions, helping cosmologists test hypotheses about the Big Bang and cosmic inflation more effectively than ever before. Neural networks, another tool from the machine learning arsenal, are applied to predict how dark matter clusters within galaxies. By training these networks on simulations, they can learn the underlying physics and then apply this knowledge to real-world data, enhancing our understanding of dark matter's role in cosmic structure formation. Artificial intelligence is also crucial for optimizing the operation of telescopes. AI systems can control the scheduling of observations, adjust settings in real time based on environmental conditions, and even predict system failures before they occur, significantly improving observational efficiency. Machine learning methods are used to process signals from gravitational wave detectors, such as LIGO and Virgo. These methods can quickly sift through noise to detect the faint signals of cosmic events, drastically reducing the time between detection and alerting the astronomical community. In radio astronomy, AI techniques are essential for filtering out the noise from the vast amounts of data collected by facilities like the Square Kilometre Array. Machine learning algorithms can distinguish between signals from celestial sources and interference from terrestrial sources, ensuring the purity of data used for cosmological research. The application of machine learning in cosmology also extends to theoretical aspects, such as parameter estimation. AI algorithms can explore the vast parameter spaces of cosmological models more efficiently than traditional grid-based methods, providing more accurate constraints on models of the universe's expansion and the properties of dark energy. AI-driven simulation frameworks are being developed to emulate the universe at various scales. These emulators can run cosmological simulations in a fraction of the time it takes traditional methods, allowing for rapid testing of theoretical models against observational data. Machine learning is also facilitating the study of cosmic evolution by enabling the analysis of time series data from variable astronomical sources. AI algorithms can detect and characterize transient phenomena like supernovae, gamma-ray bursts, and variable stars, enriching our understanding of stellar life cycles and the dynamics of the cosmos. AI technologies help in the cross-validation of data from different observational platforms, enhancing the reliability of the conclusions drawn from cosmological data. By comparing and synthesizing data from optical, radio, X-ray, and other types of telescopes, AI helps create a more cohesive understanding of observational cosmology. Predictive analytics, powered by AI, are being used to hypothesize the existence of celestial objects and phenomena before they are directly observed. This proactive approach can guide observational strategies, prioritizing targets and methodologies based on predictive models. AI is integral in managing the data lifecycle in cosmology, from acquisition and storage to processing and analysis. By automating these processes, AI reduces the time and resources required to convert raw data into actionable scientific knowledge. Moreover, AI and machine learning are driving innovation in data visualization techniques in cosmology, allowing scientists to explore complex multidimensional data sets in intuitive ways. This enhances the ability to identify trends and anomalies that might otherwise go unnoticed. In sum, the role of artificial intelligence and machine learning in cosmology is rapidly expanding, offering powerful tools for data analysis, theoretical exploration, and observational strategy. These technologies are not just auxiliary tools, but are becoming central to the way cosmological research is conducted, promising to unlock new scientific discoveries and deepen our understanding of the universe. The Euclid mission, led by the European Space Agency, is set to launch in the near future with the objective of mapping the geometry of the dark universe. By studying the shapes and redshifts of millions of galaxies, Euclid aims to better understand the role of dark matter and dark energy in shaping the universe and driving its expansion. The James Webb Space Telescope, following its launch, aims to delve into several cosmic phenomena, including the observation of the first galaxies that formed in the early universe. JWST will also study the atmospheres of nearby exoplanets, potentially identifying signs of habitability. NASA's Nancy Grace Roman Space Telescope, formerly known as WF-1, is designed to answer key questions in the areas of dark energy, exoplanets, and infrared astrophysics. With a wide-field instrument for surveys, it will advance the studies of the structure and expansion of the universe and perform a census of exoplanets to help understand the demographics of planetary systems. The Vera C. Rubin Observatory, previously referred to as LSST, will conduct a 10-year legacy survey of space and time, LSST, that will create an unprecedentedly detailed public catalogue of over 20 billion galaxies. This survey aims to address fundamental questions about the structure and evolution of the Milky Way and unveil mysterious properties of dark matter and dark energy. The Square Kilometre Array, SKA, when completed, will be the world's largest radio telescope, spread across sites in Australia and South Africa. Its vast array of dishes and antennas will explore the universe in detail never before achieved in radio astronomy, aiming to provide insights into cosmic magnetism, the nature of gravity, and the search for life beyond Earth. The Plato mission, another ESA project, is focused on discovering and studying extrasolar planetary systems, with an emphasis on identifying Earth-like planets in the habitable zone of their stars. Plato's suite of telescopes will allow for precise measurements of stellar brightnesses, enabling the detection of small dips caused by orbiting planets. The Chinese Space Station Telescope, CSST, aims to complement other space-based observatories by providing high-resolution images across a wide field of view. Its mission objectives include surveying the structure and distribution of dark matter, exploring the formation and evolution of galaxies, and detecting transient astronomical events. NASA's Dragonfly rotorcraft aims to explore Titan, Saturn's largest moon. Dragonfly will study prebiotic chemistry and extraterrestrial habitability in Titan's rich organic environment, aiming to understand the Moon's atmospheric and surface properties, potentially shedding light on the conditions that might foster life. The Bepi-Colombo mission, a joint venture between ESA and the Japan Aerospace Exploration Agency, aims to study Mercury, the least explored planet in our inner solar system. The mission's objectives include studying Mercury's magnetic field, its geology, and its extremely thin atmosphere. The Indian Space Research Organization's Aditya L1 mission will study the Sun's corona, aiming to better understand the dynamics and composition of our star's outer atmosphere. The mission will provide data crucial for understanding solar variability and its impacts on space weather, which can affect satellite communications and power grids on Earth. The Mars Sample Return Mission, a collaborative effort led by NASA and ESA, aims to collect samples from Mars and return them to Earth for detailed analysis. This mission will provide unprecedented insights into the geology and potential biosignatures on Mars, opening a new chapter in Martian exploration. The DART mission by NASA, designed for planetary defense, aims to test our ability to redirect an asteroid through a kinetic impact. This mission's objective is crucial for developing strategies to protect Earth from potential future asteroid impacts. The Jupiter Icy Moons Explorer, JUICE, by ESA, is set to explore Jupiter's large icy moons, Ganymede, Callisto, and Europa, which are believed to hold subsurface oceans. JUICE's goals include assessing these moons' potential for hosting life and better understanding the complex Jovian system. The Advanced Telescope for High-Energy Astrophysics, Athena, planned by ESA for launch in the early 2030s, will study the hot and energetic universe. It will observe large-scale structures and the processes driving galaxy evolution, focusing on black holes and how they shape the cosmos. Lastly, NASA's Artemis program aims to return humans to the Moon and establish a sustainable presence there. This initiative will serve not only as a platform for scientific research and technology demonstrations, but also as a stepping stone for future crewed missions to Mars and potentially beyond. Each of these missions represents a significant investment in our quest to understand the universe and our place within it, leveraging cutting-edge technology and international collaboration to push the boundaries of science and exploration. The expected impact of recent technological advances and upcoming missions on the crisis in cosmology is profound. These initiatives promise to provide critical data that could potentially resolve existing discrepancies in our understanding of the universe, particularly in the realms of dark matter, dark energy, and the expansion rate of the universe. Advancements in telescope technology, such as the James Webb Space Telescope, are expected to offer deeper insights into the early universe. By observing the first galaxies and stars, we hope to better understand the conditions shortly after the Big Bang, shedding light on the initial expansion phase and potentially addressing the inconsistencies related to the Hubble tension. The Event Horizon Telescope has already made significant contributions by capturing the first image of a black hole. As this project continues, it is expected to test the limits of general relativity in the strong gravity regime. Any deviations from the predictions of Einstein's theory could provide clues for new physics that might explain cosmic acceleration without the need for dark energy. Missions like Euclid and the Vera C. Rubin Observatory are specifically designed to explore dark energy and the universe's expansion through detailed surveys of billions of galaxies. By mapping the large-scale structure of the universe over vast epochs, these observatories will enhance our understanding of how dark energy has influenced cosmic history, potentially leading to a resolution of why the universe's expansion is accelerating. The square-kilometer array will probe the cosmic dawn and provide unprecedented insight into the early universe's structure. By observing neutral hydrogen and its evolution over time, SKA may reveal how the first structures formed under the influence of dark matter, offering new perspectives on this mysterious component's role in cosmic evolution. The deployment of AI and machine learning in data analysis is transforming cosmology by enabling the handling of vast datasets from these missions more effectively. These tools can uncover patterns and correlations that are not immediately apparent, potentially identifying anomalies that challenge existing models and theories. Advances in simulation technology are expected to synergize with observational data, allowing cosmologists to test various scenarios with high precision. This could lead to refinements in theoretical models of the universe, particularly those involving the interplay between dark matter, dark energy, and normal matter. Gravitational wave astronomy, buoyed by facilities like LIGO and Virgo, is opening a new window into processes that were previously unobservable. The detection of gravitational waves from black hole mergers and potentially from the early universe may offer direct evidence of phenomena that could reshape our understanding of cosmological history. The study of exoplanets and their atmospheres, as facilitated by missions like JWST and Ariel, while primarily focused on planetary science, also contributes to cosmology by improving our understanding of planetary system formation and evolution. This broadens our knowledge of physics under various conditions, indirectly informing cosmological theories. The exploration of cosmic inflation, a period of rapid expansion believed to have occurred a fraction of a second after the Big Bang, is expected to benefit from these technological advancements. More precise measurements of the cosmic microwave background, as expected from future missions, could provide definitive evidence of inflationary models. Efforts to map the cosmic microwave background with greater accuracy and over larger areas of the sky will refine our understanding of the early universe's temperature fluctuations. This is critical for testing the predictions of the Big Bang model and understanding the quantum fluctuations that may have seeded large-scale structure. Astrophysical phenomena, such as supernovae, neutron star mergers, and black hole accretion processes, are being studied with increasing detail. Understanding these extreme events can provide indirect clues about the nature of dark matter and energy, as these components influence the structure and evolution of the cosmos. The integration of observational cosmology with particle physics through data from particle accelerators and cosmic observatories is fostering a more holistic view of the universe's laws. This interdisciplinary approach is crucial for tackling the cosmological crisis, as it allows for the validation of theories across different physical scales and environments. New methods of indirect observation, such as using quasars and gamma-ray bursts as standard candles, are enhancing our ability to measure cosmic distances and expansion rates across the universe. This could provide new insights into the rate of expansion at different times in cosmic history, addressing the Hubble tension directly. Overall, the convergence of new technologies, missions, and theoretical insights is poised to significantly impact the crisis in cosmology. By providing a deeper and more comprehensive understanding of the universe, these developments hold the promise of resolving long-standing questions and potentially uncovering new physics that could revolutionize our view of the cosmos. Resolving the crises in cosmology could fundamentally transform our understanding of reality, offering profound insights into the nature and origins of the universe. By addressing discrepancies such as the Hubble tension and the mysteries of dark matter and dark energy, we could reach a new level of comprehension about the cosmos. Achieving a resolution to these crises would likely require a paradigm shift in physics, akin to the revolution brought about by Einstein's theory of relativity. Such a shift would not only reconcile the discrepancies in current observations, but might also unify the forces of nature in a single theoretical framework, potentially leading to a long-sought theory of everything. Resolving the nature of dark matter could redefine our understanding of matter itself, revealing new forms of matter with properties that challenge conventional physics. This could have wide-ranging implications, from the fundamental forces that govern the universe to practical applications in technology, materials science, and energy. Understanding dark energy and its role in the accelerated expansion of the universe could lead to new insights into the fate of the cosmos. It could tell us whether the universe will continue to expand indefinitely, end in a big crunch, or reach some other unforeseen conclusion. Clarifying the reasons behind the Hubble tension might lead to adjustments in our measurements of the universe's expansion rate, which could recalibrate the cosmic distance ladder and affect everything from age estimates of the oldest stars to the understanding of cosmic geography. A deeper understanding of the early universe, particularly through resolving issues around cosmic inflation and the Big Bang singularity, could provide unprecedented insights into the conditions that prevailed at the very beginning of time, potentially shedding light on the ultimate origin of the universe. Resolving these cosmological crises could also enhance our understanding of fundamental physics, providing clues that lead to the discovery of new particles, forces, or phenomena that bridge the gaps between quantum mechanics and general relativity. On a more philosophical level, resolving the cosmological crises could change our perspective on our place in the universe. Understanding the true nature of the cosmos might alter our philosophical and existential frameworks, influencing everything from the search for meaning to the pursuit of science itself. The potential resolution of these crises could lead to technological innovations, as new theories and materials are developed based on our enhanced understanding of the universe. This could drive new industries and applications, from quantum computing and energy production to space travel and communications. Educationally, a resolution could revolutionize science curricula, with new theories and concepts becoming fundamental to our understanding of physics, much like how relativity and quantum mechanics have become cornerstones of modern science education. Such a resolution could also have implications for the search for life beyond Earth. By understanding the cosmological parameters that govern planetary formation and the distribution of galaxies, we could better predict where and how life might arise in the universe. Resolving these crises would likely lead to more accurate and reliable methods for observing and measuring cosmic phenomena. Enhanced tools and techniques that arise from new theoretical insights could open up further areas of inquiry that are presently beyond our reach. In the context of environmental science, a better understanding of cosmic phenomena could inform our understanding of Earth's place in the universe, potentially contributing to models that predict meteorological and geological phenomena influenced by cosmic events. On a global scale, the collaborative nature of addressing these cosmological questions could serve as a model for international cooperation in science, demonstrating how shared intellectual pursuits can unite diverse groups of people across national and cultural boundaries. Finally, resolving these cosmological crises would underscore the dynamic and ever-evolving nature of scientific inquiry. It would remind us that science is an ongoing journey of discovery, where answers often lead to new questions, and the pursuit of knowledge is a never-ending quest driven by human curiosity and creativity. Resolving current cosmological crises could catalyze transformative changes across physics and astronomy, shifting paradigms and opening new frontiers of inquiry. These fields are deeply intertwined, and advancements in our understanding of the cosmos invariably influence foundational concepts in physics, while expanding the scope of astronomical exploration. In physics, uncovering the nature of dark matter could revolutionize particle physics, potentially introducing new particles that don't fit within the current standard model. This discovery would necessitate a re-evaluation of the fundamental constituents of matter, possibly leading to the development of a more comprehensive model of particle interactions. Similarly, a deeper understanding of dark energy and its implications for the expansion of the universe might lead to significant advancements in field theory. Theories that successfully integrate dark energy could provide new insights into the vacuum energy of space and its role in the cosmological constant, a central issue in theoretical physics. Resolving the Hubble tension could lead to refinements in the measurement techniques used across astronomy and physics, enhancing the precision of distance measurements and the determination of fundamental constants. This precision is crucial for testing theories in both experimental and observational settings. The potential integration of quantum mechanics and general relativity into a unified framework would not only resolve a major theoretical challenge in physics, but could also lead to technological breakthroughs in areas like quantum computing, gravimetric sensing, and space-time-based navigation systems. In astronomy, solving these cosmological puzzles would dramatically improve our models of cosmic evolution. This could lead to more accurate predictions about the behavior of galaxies, the formation of stars, and the life cycle of cosmic structures from superclusters to black holes. Astrophysics could see significant impacts from these resolutions, particularly through enhanced understanding of high-energy phenomena like gamma-ray bursts, neutron-star collisions, and black hole mergers. These events offer a glimpse into the most extreme conditions in the universe, where the interplay between gravity and quantum mechanics is critical. The field of exoplanet research could also benefit as improved cosmological models refine our understanding of planetary system formation. This could influence our search for life beyond Earth by identifying the most likely places where it could exist and informing the design of missions to explore these worlds. Technological advances driven by cosmological research, such as improved sensors and telescopes, could be applied in other areas of science and engineering. For example, technologies developed for space telescopes could enhance terrestrial imaging systems used in everything from medical diagnostics to environmental monitoring. In theoretical physics, new cosmological insights could inspire fresh approaches to long-standing problems like the unification of forces, the nature of time, and the origins of the universe. Each resolution brings with it a cascade of new questions and theories, perpetuating the cycle of discovery. Educational impacts are also likely, as changes in fundamental theories would alter the content and focus of science curricula at all levels. This could inspire a new generation of scientists with a revised understanding of what the universe is and how it works. The field of computational physics would also evolve, as new theories would require new types of simulations. Innovations in computing necessary to explore these new theories could spill over into other fields that rely on complex simulations, such as climate science and economics. Interdisciplinary fields like astrochemistry and astrobiology would also see growth from a better understanding of cosmology. Knowledge about the distribution of elements and conditions in the early universe could inform studies on the origins of life and the types of chemical processes that are possible in various cosmic environments. In terms of observational technology, the astronomy field might develop next-generation instruments designed to observe phenomena predicted by new theories, or to improve the resolution and range of current observations, further fueling the cycle of discovery. Finally, these potential changes in physics and astronomy would likely foster greater public interest and engagement with science. As fundamental aspects of our understanding of the universe shift, the resulting discussions and debates would reach beyond academic circles, enhancing science communication and education. These dialogues can increase support for science, influence policy decisions, and cultivate a more scientifically literate society. The philosophical impact of discoveries in cosmology extends far beyond the boundaries of science, touching on profound questions about existence, the nature of reality, and our place in the universe. Each major breakthrough in understanding the cosmos reshapes not only our scientific worldview, but also our philosophical and existential frameworks. The realization that the universe began with a Big Bang challenges classical notions of time and causality, prompting philosophers and cosmologists alike to ponder what, if anything, came before the Big Bang, and whether the universe had a beginning in time or if it cyclically expands and contracts. Discoveries of the vastness of the universe and the multitude of galaxies within it have led to a Copernican-like shift, reinforcing the idea that Earth and its inhabitants are not central to the workings of the cosmos. This has profound implications for anthropocentric philosophies and religions. The concept of an expanding universe that might be accelerating due to dark energy introduces questions about the ultimate fate of the cosmos, whether it will expand forever, end in a big freeze, big rip, or eventually begin to contract. These scenarios invite philosophical inquiry into the meaning of an impermanent universe. The possible existence of other universes within a multiverse raises questions about the uniqueness of the laws of physics in our own universe. If different physical laws are possible, philosophers might question the foundations of necessity and contingency in nature. The nature of dark matter and dark energy, constituting most of the universe's mass energy yet remaining undetectable except by their gravitational effects, challenges our understanding of what it means for something to exist. If entities are known only by their effects on other entities, this could revise our concepts of evidential existence. The search for extraterrestrial life and the study of exoplanets in cosmology extend the philosophical debate about life's rarity and value. Discovering life elsewhere could profoundly affect our ideas about life's meaning and purpose on Earth. Quantum cosmology, which attempts to describe the universe at its earliest moments, intersects with philosophical discussions about determinism and randomness. The role of probability in the fundamental structure of reality leads to questions about predictability and the nature of scientific explanation. The anthropic principle, which is often cited in cosmological context to explain why our universe appears finely tuned for life, generates debate among philosophers about the roles of observation and measurement in defining laws of nature. This principle challenges objective views of the universe, suggesting our understanding is inherently biased by our presence as observers. Cosmological discoveries also impact our ethical considerations. Debates about space exploration, planetary protection, and the future colonization of other planets involve ethical questions that are informed by our understanding of the universe and our responsibilities within it. The advancements in cosmology encourage a rethinking of the classical philosophical problem of space and time. Understanding that space and time are interconnected and dynamic, qualities described by general relativity, contrasts sharply with Newtonian views of absolute space and time, altering how philosophers consider the framework of reality. Cosmological studies also raise the question of finitude versus infinitude. Whether the universe is finite or infinite impacts numerous philosophical and theological debates about the nature of infinity, the possibility of an actual infinite, and the limits of human understanding. In a broader cultural context, cosmological discoveries influence how society at large thinks about progress, the future, and technology. As we learn more about the universe, these discoveries often symbolize human achievement and potential, shaping cultural narratives about where humanity is headed. Philosophical discussions about simulation theories are fueled by advances in cosmology and technology. The idea that our universe might be a simulation posits intriguing questions about reality, consciousness, and the possibility of higher-order beings, reflecting age-old philosophical inquiries in modern terms. Finally, the ongoing quest to understand the universe reflects the philosophical essence of human curiosity and the desire for knowledge. The pursuit itself, regardless of the answers found, underscores a fundamental aspect of human nature and philosophy, the relentless drive to explore and understand our environment. Ethical considerations in cosmology encompass a range of issues, from the allocation of funding and resources to the broader implications of astronomical discoveries. These issues are integral to the development and direction of research within the field. One primary ethical consideration involves the allocation of substantial public or private funding to cosmology. Given that cosmological research often requires expensive equipment and lengthy timelines, it raises questions about the prioritization of scientific research, especially when compared to more immediate global needs such as health, poverty, and environmental sustainability. The pursuit of knowledge about the universe must also consider the environmental impact of constructing and operating large astronomical facilities. These projects often require significant land use and energy consumption, and their environmental footprint must be weighed against the scientific benefits they provide. There is also an ethical duty to ensure that the data and discoveries in cosmology are shared openly and fairly within the scientific community and with the public. The principle of open access to scientific data promotes transparency and broadens the impact of research by enabling scientists from around the world to contribute to and benefit from new findings. Ethical considerations extend to the cultural and sacred significance of sites often chosen for astronomical observatories. For example, the construction of telescopes on Mauna Kea in Hawaii has faced opposition from native Hawaiian groups who consider the land sacred. Respecting indigenous rights and cultural heritage is a critical ethical concern in such cases. The potential detection of signals from extraterrestrial intelligence poses profound ethical questions regarding how humanity should respond. The formulation of a careful response that considers the global impact of such a discovery is crucial. This involves international cooperation and dialogue to develop protocols that respect diverse viewpoints and potential global repercussions. Ethical funding practices in cosmology also involve considerations of equity and inclusion. Ensuring that research opportunities, funding, and resources are accessible to a diverse range of scientists, including those from underrepresented groups and developing countries, is essential for fostering a more inclusive scientific community. The pursuit of cosmological research carries with it the responsibility to avoid militarization of space. As technologies developed for cosmological research could potentially be applied to military uses, maintaining a clear ethical boundary is essential to prevent the escalation of arms in space. Researchers must also navigate the ethical landscape of communicating their findings to the public. This involves avoiding sensationalism, especially in media representations, which can mislead the public about the implications of cosmological discoveries. Accurate and responsible communication is crucial. The long-term nature of many cosmological projects, such as those aiming to answer fundamental questions about the universe, requires sustained funding that might span decades. Ethical considerations about such long-term investments involve assessing the balance between potential groundbreaking discoveries and the opportunity cost of not investing in other scientific areas. There is also the ethical responsibility to educate and inspire the public about cosmology. Public engagement helps justify the large expenditures on cosmological research by demonstrating its value in enriching our understanding of the universe and our place within it. In dealing with unknown entities such as dark matter or energy, ethical science practice involves maintaining a stance of humility and openness to new ideas. The acknowledgement of what we do not know guides a responsible approach to theorizing and experimentation. Ethical considerations in cosmology should also address the potential for international conflict over shared resources and research findings. Promoting cooperative international frameworks for research and discovery can help mitigate these conflicts. The implications of cosmological research on philosophical or existential beliefs also warrant ethical consideration. The potential for scientific discoveries to challenge or change human perspectives on life and the universe should be approached with sensitivity and respect for diverse beliefs. Lastly, cosmological research, like all science, must be conducted with integrity, avoiding biases and conflicts of interest that could undermine the reliability of research outcomes and public trust in science. Upholding these ethical standards is essential for the continued advancement and societal support of cosmology. Today, we convene a distinguished panel of cosmologists, theoretical physicists, and philosophers to discuss the ongoing crises in cosmology. This forum aims to explore the various challenges facing the field, from the tension in the Hubble constant measurements to the mysterious natures of dark matter and dark energy. Our panel includes leading experts in cosmology who have spent their careers studying the large-scale structure of the universe. They bring insights into the latest observational data and theoretical models that address the expansion of the universe and its implications for the standard cosmological model. Joining them are theorists who specialize in the mathematical frameworks that underpin cosmology. They offer perspectives on alternative theories of gravity, modifications to the standard model of particle physics, and the potential unification of quantum mechanics with general relativity. We also have philosophers of science who will help us navigate the philosophical implications of these cosmological questions. Their analysis will cover the impact of cosmological discoveries on our understanding of reality, the concept of existence, and the methodology of science itself. The panel will begin by addressing the Hubble tension, a discrepancy in the rate of the universe's expansion as measured from the early universe compared to its measurement from the local universe. The discussion will explore the potential implications of this tension for our understanding of cosmology and physics. Following this, our experts will delve into the enigmatic components of our universe, dark matter and dark energy. They will discuss the evidence supporting these concepts, the challenges in detecting them, and the theoretical alternatives that might explain the phenomena attributed to them. The conversation will then turn to the role of new technologies and instruments in cosmology. Panelists will discuss how advancements such as the James Webb Space Telescope and the Event Horizon Telescope may provide new data that could help resolve existing cosmological puzzles. A significant portion of the discussion will focus on the philosophical challenges posed by modern cosmology. This includes debates over the criteria for scientific theory acceptance, such as falsifiability and predictability, and the role of aesthetics and simplicity in theory selection. The theorists on the panel will explore the potential for new physics at the intersection of quantum mechanics and gravity. They will discuss how upcoming experiments and theoretical breakthroughs could reshape our understanding of these fundamental forces. Our philosophers will raise questions about the implications of potentially discovering a multiverse. They will discuss how such a discovery could affect traditional notions of scientific truth and our understanding of the universe as a comprehensible and singular entity. The panel will also consider the ethical aspects of cosmological research, discussing the responsibility of the scientific community in conducting and communicating their research. This will include the allocation of resources and the environmental impact of large astronomical observatories. As the discussion opens up to audience questions, our panelists will engage directly with both the scientific community and the interested public. This segment will provide an opportunity to address common misconceptions and public curiosities about the nature of the universe. In closing, the panel will reflect on the future of cosmology as a discipline. They will discuss the upcoming missions and experiments that are likely to redefine our understanding of space, time, and matter. The goal of this panel discussion is not only to elucidate the current crises in cosmology, but also to foster a broader dialogue about the role of cosmology in our collective quest for knowledge. This dialogue aims to bridge the gap between complex scientific issues and public understanding. Finally, the panelists will provide their thoughts on the philosophical and scientific mindset needed as we approach the frontiers of cosmic knowledge, emphasizing the importance of maintaining an open and critical approach to exploring the cosmos. This perspective is vital for advancing cosmology in the 21st century and beyond. Throughout our discussion, we have explored several major crises in cosmology, each presenting unique challenges and opportunities for advancing our understanding of the universe. The first of these crises involves the Hubble tension, a discrepancy between the rate of the universe's expansion, as measured through observations of the early universe and calculations based on the local universe. This unresolved issue challenges the consistency of the standard cosmological model and suggests that new physics might be necessary. We delved into the enigmatic nature of dark matter, an invisible substance that does not emit, absorb, or reflect light, yet exerts a significant gravitational influence on galaxies and galaxy clusters. Despite its pivotal role in the cosmological model, dark matter has eluded direct detection, prompting debates over its existence and nature. Dark energy, another cornerstone of the standard model of cosmology, was discussed for its role in accelerating the expansion of the universe. The mysterious force opposes the gravitational pull that should slow this expansion, yet its fundamental properties remain poorly understood, challenging existing theories of physics. As we reflect on the crises and theories discussed today, several potential solutions and future directions emerge for advancing cosmology. These approaches aim to resolve the fundamental questions and discrepancies currently facing the field, paving the way for a deeper understanding of the cosmos. One promising solution to the Hubble tension involves refining our measurements of the expansion rate of the universe. Future missions and improvements in technology, such as more precise distance ladders and better calibration of standard candles, could provide more consistent data and potentially reconcile the discrepancies between measurements at different cosmic scales. In the quest to understand dark matter, upcoming particle physics experiments, such as those conducted at the Large Hadron Collider and other underground detectors, may finally detect dark matter particles directly. Alternatively, advancements in astronomical observations could confirm the presence of dark matter through its gravitational effects on visible matter in new and more conclusive ways. The mystery of dark energy might find resolution through detailed observations of the large-scale structure of the universe and the distribution of galaxies. Missions like the Euclid spacecraft and the Vera C. Rubin Observatory are designed to map billions of galaxies, providing insights into how dark energy has influenced the expansion of the universe over time. Theoretical physicists continue to explore modifications to general relativity, such as FR, gravity, and scalar tensor theories, to see if these can better explain cosmic acceleration without the need for dark energy. These alternative theories could be tested by precise measurements of cosmic microwave background radiation and galaxy clustering. String theory remains a significant area of research, with theorists working to derive testable predictions and potential signatures of extra dimensions or supersymmetric particles. Future particle accelerators and cosmic observations might uncover evidence that supports or refutes string theory's broader claims. The multiverse theory may be explored further through statistical analysis of cosmic microwave background radiation or the distribution of physical constants in our universe. While direct evidence may remain elusive, indirect signatures or theoretical consistency with other areas of physics could lend credence to this bold framework. Philosophical and foundational considerations will continue to guide the interpretation of cosmological data. As new theories are proposed, their philosophical implications must be considered, ensuring that these theories do not only fit the data but also cohere with broader epistemological principles. Ethical considerations will also shape future directions in cosmology. As the field continues to require significant resources, the scientific community must balance these demands with the broader needs of society, ensuring that cosmology contributes to human knowledge while respecting our ethical obligations to the present and future generations. Technological innovations will undoubtedly play a critical role in addressing cosmological questions. The development of new sensors, telescopes, and computational methods will enhance our ability to collect and analyze data from the farthest reaches of the universe. The integration of machine learning and artificial intelligence in data analysis will accelerate the discovery process, helping cosmologists sift through vast amounts of data to identify patterns and anomalies that may lead to breakthroughs in understanding the cosmos. Educational initiatives will also be important, as a well-informed public and a new generation of scientists are essential for the sustained support of cosmological research. These efforts will help cultivate a deeper appreciation for the science of cosmology and its role in answering fundamental questions about our existence. International collaboration will be crucial, as the scale of cosmological questions often requires resources and expertise distributed across the globe. By sharing data, ideas, and funding, the international scientific community can tackle these profound questions more effectively. Continued philosophical inquiry into the implications of cosmological discoveries will enrich our understanding of the universe. This includes exploring the metaphysical, existential, and ethical implications of concepts such as the multiverse, dark matter, and the potential finiteness or infiniteness of the universe. In summary, the future of cosmology lies in a multidisciplinary approach that blends advanced technology, theoretical innovation, philosophical depth, and public engagement. By exploring these diverse paths, cosmology can move closer to resolving the current crises and uncovering the deeper truths of our expansive universe. Lastly, whatever solutions and directions the future holds, the pursuit of knowledge in cosmology will continue to inspire awe and wonder about the vastness and complexity of the cosmos, reminding us of the perpetual mystery and beauty of the universe we strive to understand. Cosmology is a profound scientific discipline that extends beyond the mere study of the stars and galaxies to address the very origins, structure, and fate of the universe itself. Its importance lies not only in its scientific endeavors, but also in its ability to inspire and challenge our understanding of existence. Reflecting on the history of cosmology offers a deep appreciation of how our perception of the universe has evolved. From the ancient models of the cosmos as a simple geocentric structure, to the modern understanding of a vast, expanding universe, cosmology has continually reshaped our view of our place in the cosmos. The study of cosmology serves as a bridge between various domains of physics. It connects quantum mechanics, which governs the smallest particles, with the laws of general relativity, which dictate the dynamics of galaxies and the universe, creating a comprehensive picture of physical reality. In addressing fundamental questions such as the origin of the universe and the nature of its constituents, cosmology directly engages with philosophical and existential issues. It challenges us to consider the beginning of time, the universe's ultimate fate, and the laws that govern its evolution. Cosmology's quest to understand dark matter and dark energy touches on the limits of human knowledge and technology. These mysterious components, which make up most of the universe, remind us of the vastness of the unknown and the potential for future discoveries that could revolutionize our understanding. The importance of cosmology also lies in its ability to foster international collaboration. It is a field that inherently requires global cooperation, as the universe's secrets are not bound by national borders. This collaborative spirit is essential for advancing our collective scientific knowledge. Cosmology also plays a critical role in technological innovation. The instruments and methods developed for cosmological research, such as advanced telescopes and observational techniques, often find applications in other scientific fields and even in everyday technology. The field encourages a unique perspective on Earth and humanity. By studying the universe, we gain insight into the fragility and rarity of our planet, which can foster a greater appreciation for our world and motivate actions to protect our environment. Cosmology's influence extends to education, where it serves as a gateway to science for many students. The study of the cosmos sparks curiosity and wonder, drawing more young minds into careers in science, technology, engineering, and mathematics. In a broader sense, cosmology raises awareness about the scale and complexity of the universe. It challenges our cognitive and imaginative limits and enhances our appreciation for the beauty and intricacy of the cosmos. The field of cosmology holds a mirror to our worldviews, reflecting how they change in light of new discoveries. Each cosmological breakthrough has the potential to alter profoundly how we think about nature, reality, and our own beliefs. By continuing to explore the cosmos, cosmology not only satisfies human curiosity, but also fulfills a deep-seated need to understand our origins and our place in the universe. This quest for knowledge is a fundamental aspect of human nature. Cosmology also has a unifying effect on humanity. It is a reminder of our shared origin and destiny within the vast expanse of the universe, promoting a sense of unity and purpose that transcends individual differences. In practical terms, cosmology's pursuit helps to refine our abilities in problem-solving, modeling, and critical thinking. The challenges of cosmological research develop skills that are invaluable across many fields and disciplines. Lastly, reflections on the importance of cosmology bring us back to the core of scientific inquiry, the balance between knowing and wondering. As we expand our knowledge, we also deepen the mystery, continuously driving the cycle of discovery that is both humbling and exhilarating. Now, as we wrap up our discussion on the profound mysteries of cosmology, I want to encourage each of you to engage further with this captivating field. Whether you're a seasoned researcher, a curious student, or simply someone fascinated by the cosmos, there are countless ways to delve deeper into the wonders of cosmology. One of the most accessible ways to engage with cosmology is through educational resources. Take advantage of online courses, documentaries, and popular science books that offer engaging explanations of complex cosmological concepts in accessible language. For those seeking a more hands-on approach, consider participating in citizen science projects. These initiatives allow enthusiasts of all ages and backgrounds to contribute to real scientific research by analyzing data, classifying galaxies, or even discovering new astronomical phenomena. Don't hesitate to join local astronomy clubs or attend public lectures and stargazing events in your area. These gatherings provide opportunities to connect with fellow enthusiasts, learn from experienced astronomers, and observe celestial objects through telescopes. Social media platforms offer vibrant communities of cosmology enthusiasts where you can share your thoughts, ask questions, and stay updated on the latest discoveries. Engaging with these online communities can foster meaningful discussions and inspire new avenues of exploration. If you're a student considering a career in science, don't underestimate the value of pursuing studies in physics, astronomy, or related fields. The journey to becoming a cosmologist begins with a solid foundation in mathematics, physics, and computational science. For educators, integrating cosmology into classroom curricula can ignite students' curiosity about the universe and inspire them to pursue careers in science. Incorporating hands-on activities, multimedia resources, and guest speakers can enhance students' understanding and appreciation of cosmological concepts. Parents can also nurture their children's interest in cosmology by introducing them to age-appropriate books, documentaries, and interactive learning experiences. Encouraging curiosity and exploration from a young age can lay the groundwork for a lifelong passion for science. Remember that cosmology is a field that welcomes enthusiasts from all backgrounds and levels of expertise. Whether you're an amateur astronomer, a professional scientist, or simply someone who marvels at the night sky, there's a place for you in the world of cosmology. As you embark on your journey of exploration, don't be afraid to ask questions, challenge assumptions, and embrace uncertainty. Cosmology is a dynamic and evolving field, and every question you ask brings us one step closer to unraveling the mysteries of the universe. Take advantage of the wealth of resources available online and in your local community to deepen your understanding of cosmology. Attend lectures, workshops, and conferences whenever possible to immerse yourself in the latest research and discoveries. Consider supporting organizations and institutions that promote scientific research and education in cosmology. Your contributions can help fund groundbreaking research, support outreach initiatives, and inspire the next generation of cosmologists. Above all, approach cosmology with a sense of wonder and awe. The universe is vast and mysterious, filled with countless wonders waiting to be discovered. By engaging with cosmology, you become part of a centuries-old tradition of exploration and discovery that has transformed our understanding of the cosmos. So, whether you're gazing up at the night sky from your backyard or poring over the latest research papers in cosmology, remember that you are a vital part of humanity's ongoing quest to unlock the secrets of the universe. Embrace the journey, and let the wonders of cosmology inspire you to reach for the stars.